Good morning. Only if anyone here is in Sydney, or even from what I can tell, other parts of Australia, uh, the mistake I'm making today is not the fact that it's morning or not, but the fact that it is good. I'm just looking out the window at the moment, and the trees are waving around like they're in a 1990s nightclub. Um, and this has definitely got to be one of those days where I dub this, for those of you in Australia, I dub this the "Aren't We Glad We're All Working From Home" edition of COMP1511 lectures. This is going to be the day of all days that I think most people are going to potentially have the laptop in bed and have not crawled out from under the covers at the moment. Well, Matthew Bryan is saying rain is the best weather, get out of here. Andrew is saying good for me as well. John's saying that your cat couldn't open her cat door because the wind was too strong. I feel sorry for that poor cat, but I mean, like, honestly, probably probably better for the cat to just hang out indoors on a day like today. Andrew is saying that you lived your whole life in the desert, so you love this weather. That's kind of nice. And I mean, also, with this kind of drought that's been going for such a long time in Australia, it's pretty nice to get a bit of rain. I have a feeling that farmers would prefer a more even distribution of rain rather than a massive dump in a storm. But you're not going to argue against it when it arrives. So hopefully this does some good somewhere. For those of us who aren't involved in anything like that, though, it's the kind of weather you just sort of don't want to go outside. It isn't too bad because there's not that much to do outside right now anyway. I don't know how COVID's going where you are, but anyone here is in Melbourne. Well, you can't really do anything outside anyway. Everything's shut again. We're starting to see a few spikes around Sydney as well, so we're starting to think about whether there's a second wave coming here. I actually got tested on the weekend because I had a cough that came on Thursday or Friday, and actually you can still hear it in my voice a little bit. So I got myself swabbed. Happy to say I don't have COVID, so I'm very, very safe at the moment in terms of like knowing for sure that I don't have COVID as of Saturday, I think, when I got checked. Mason is saying, imagine going outside in the first place. That was a funny jokes going around about people saying that there's a significant percentage of the population who just didn't notice when the lockdown happened because everyone else just locked down, but they've been sort of in self-imposed isolation for quite some time. Lachlan is asking me to talk like Borat the whole lecture. Yes, we do lecture. Let's not, though. I mean, like, I have a feeling there's like some stuff about Borat which is okay, and some stuff about Borat which is a little bit racist, so I probably shouldn't even have started that at all. Okay, I mean, I guess you're just pointing out the fact that my voice has changed a little bit because I've been coughing for most of the weekend. One thing I did want to talk about, I don't want to leave this unsaid, but over the weekend, and I know that this probably, hopefully, isn't such a big deal, but for some people it might be a big deal, is that I found a YouTube video, and I had a look through it, and it was a significant amount of a solution for the first assignment that was publicly available. Can't say I was too happy about that. But I'm going to be honest about this, is that it's going to happen. I mean, it's not usually as openly publicized as something that, like, a public YouTube video that just anyone can watch, that basically, it breaks the one rule, right? You know, I had one rule for this course where I said no one takes away anyone else's education. This one most certainly does that. So yeah, there's a like sort of. I guess it's okay now that it's past the due date. I can talk about this. I didn't really want to say anything about it beforehand, but I mean, there's still some people working on the assignment, especially anyone who has extensions or anything like that. It's a real awkward situation, right? Because like having a video like that out there makes people really, really tempted to watch it. And so like what I want to say is like I think that we need to, when we're working on an assignment or a piece of work, like this the same person's got a whole bunch of weekly tests up there, which I noticed have been published before the deadline, which really, really kills the idea. So what I want people to think about when you know that this stuff is available, and we've had it other times, usually not quite as malicious as this situation. We've had a lot of other times where I teach people about the potential use of starting your own Git repo and putting things in Git. And so people go, oh, that's a really cool idea. I'm going to store all of my work in Git so that I've got a backup and I've got, I can track my work as it's happened. And so when we've got things like that, occasionally people will leave them on public by accident, and they don't realize they're actually just sort of broadcasting to the world the solutions to all of the labs and tests and things like that. And what they're doing is they're breaking the rule that I have, which is like you're taking other people's education away from them, because if they just copy from what you've got there, they're never going to have worked through everything. So the one thing that I always want us all to think about is, why are we doing an assignment? And why are we doing something like a weekly test or a lab exercise or something like that? And for me, the answer that I would love everyone to have is, I'm doing this assignment because there's something I want to learn about this. I'm doing this assignment because I trust that the subject has put together this assignment not... See... Funny thing, I didn't actually write the assignment so that someone would write Freefall for me. I don't actually have plans to publish Freefall as a game, so I didn't actually need your answers to the assignment. So I'm not worried about whether a student does it or doesn't have the answers to Freefall. What I would like is for everyone to go through the process of building it from scratch, because the whole reason the assignment exists as it is, why it's in stages, why it's in escalating difficulty, why it goes around and checks different capabilities that you can do, is that by the end of the assignment, wherever you got to in the assignment, you've learned something useful out of it. And I really couldn't care less how much of it anyone finishes or anything like that. I don't need people to complete the assignment. What I want most for people is to have worked through it and gotten something out of it. So when there's a YouTube video that works through the entire assignment, and you could just watch the video, and as you're watching it, type in the assignment and get a quite a good result in terms of the marks you get from the assignment, you're going to get very little out of the learning from the assignment by doing that. So that's one of the issues that I have, is that people publishing these entire walkthroughs and stuff like that is really, I mean, it's not going to affect people who want to do this. It's not going to affect people who are like seriously dedicated to doing the subject, but it is going to affect a lot of people who hit that point of like, oh, I'm really scared that I'm not going to pass this. So instead of working through it, they just go and copy stuff down, and then you end up with this situation where it's actually worse for those students, because if you have copied and just used someone else's work, you end up kind of in a state where you're pretending that you know something that you don't. I would personally much prefer to know for sure how much I know about something rather than to pretend that I know more about something than I do. Because pretending you know more about something just pushes you into a situation where there's just a trap waiting for you in the future, where someone else is going to be like, alright, you did fine, you obviously passed that other subject, so you know what you're doing, let's continue. Sometimes, especially at a first year level, it's better to fail something and get more time to do it. But, you know, I could say that a lot, and I'm sure that some people aren't going to listen to me anyway. So for those people, bear in mind that I have the code um, from from people who are solving it online. So we obviously have already checked how many assignments people have submitted that match the code that's in the videos online and in the Git repo that they've got. So just like if you've had a change of heart and you're like, look, I used that thing and I understand that I've now created an assignment that's not my own work, and I would like to maybe rescind my submission of this assignment before you kick me out of the uni for cheating or something like. I'm not going to kick you out of the uni, but still, it's kind of. I think it's better to just fail something honestly than for me to go chase you down after the course is finished and say, I've noticed that your assignment code is exactly the same as someone else's, because you both copied from the same thing. And now it's even worse because I actually have the code that was publicized online, and that's going to go into the system we use to check for cheating, so it's going to be really obvious who's used it and who hasn't. So if you do want to have a chat about this and you want to say, look, I feel like maybe I haven't done the right thing in this first assignment, reach out to us. You can email me on the CS1511 address for this kind of thing and just go, look, I think maybe I didn't do this right, and I do understand, and I'd like to make this better. We can talk about this, right? I'm not gonna bring the band hammer down on everyone, because this is just so. I haven't had this in the past actually. If someone just goes so public with it and just go, here's COMP1511, and here's all the solutions to everything, and here's how we can just kind of. It's weird because I think on some weird scale of what they're thinking, they're trying to help people, but yeah, it's awkward because I'm also trying to help people, and doing stuff like that's really disrupting the message. It's making it really difficult for me to help people properly. So yeah, we'll see where we go with this, and I know that the majority of the time you'll just kind of be on track and doing things, but it's really not about those times that's important. Sometimes it's the times when you're at your moments of your most desperation. You're like, I just have to pass this, and I'm going to do anything I can to pass this, and that's where you reach out to things like that, and that can cause problems. So just, I don't know, I just want to leave you that kind of message. I think the most important thing for everyone to remember is, why are you doing this subject? If you're doing this subject because you just want to pass it and you really don't care about it, then you should probably just sort of, I don't know, personally, if I ever got into that situation where I was like, I have to pass it and I don't have a choice, and it's all just kind of like, and I don't really want to be here, that's the point where I would say, take a term off uni, take 2 terms off, go do something that doesn't put a lot of pressure on you, and figure out what you want to do with your life, and then come back. Because if you don't want to do it, if you're not doing it because you have a goal or an aim that you're going towards, then it's just sort of never gonna work that well anyway. And if you're doing university because you have a goal, you're like, I want to be a software engineer, then cheating in your assignments is like stealing from yourself. So it's going to end up in a situation where if you do want to be a software engineer eventually, obviously you're going to put the work in, so that you can be, rather than setting up a situation where you go on to subjects that are much harder than this one without the foundational knowledge that this subject was supposed to give you to prepare you for those things. So yeah, I don't want to go too deep into this because this is lecture time, and what I really should be doing is teaching the students who care about what they're doing, but I want to at least have this message out there because this is not the last time this is going to happen. All the way through your university career, you're going to be given these kind of continual kind of temptations to get a free ride. But understand that the free ride doesn't gain you anything. It just pushes you further along in your degree with less knowledge. which I would consider to be a negative. But up to you. I will let you judge what you want to do based on what your goals are. I'm sure there's some people there who whose goals are, I need to get enough marks to get through this degree so that I can move on to something else, and the knowledge gained is not actually necessary. I have other plans. I don't know what they might be, but you have your own plans, right? So do whatever you feel you need to do to get to your goals. I'm not actually, no, I'm going to say do whatever you need to get to your goals. Just trample everyone else along the way. Yeah, don't do that. Do what you feel you need to do to get to your goals, but don't just, like, try not to disregard the overall context of what you're doing, because you're trying to learn something. Well, at least I hope you're trying to learn something. Anyway, that's what I wanted to say about that. I know it's everywhere, because someone pinged me to let me know that the links went out on the Facebook chat for 1511 as well. I heard some really funny quotes. It's like people like, "Ooh, Mark is going to be pissed about this," and it's like, yeah. First reaction's always like, for me, seeing something like that, first reaction's always anger, but then I'm just like, okay, chill back off the anger, because that's never that positive. But what I want to say is at least give a message to people who are making a genuine attempt at the subject, and you know already that this thing's not going to help you. So the trick is having the willpower to know that it's not going to help you at the time where you need the most help. So as always, I want to say that we're open for help. I was really proud of our tutors on the forum, because even at peak times in the assignment, they got the response time on average to be less than 12 hours in response, which is pretty amazing when you've got basically 2 or 3 people answering questions, and there's like 100 questions in a day, and they're managing that kind of response time. So they did a really good job there, and I hope that was helpful for anyone who went to the forum for some official advice rather than going somewhere else where someone doesn't know the limit of how much advice to give you before they've taken away your chance to actually learn something from it. Okay, so what do we got? There's a lot of stuff in chat there. I'll just scan through it. Quoty saying the assignment got you burned out, not gonna lie. Yeah, I totally understand. We're now in the gap, so we've got a week gap before the next assignment is released. So hopefully this is a point to chill. I was gonna say that if you don't need to have finished the whole assignment, so try not to push yourself all the way out to burnout. Like, a lot of these assignments, the way we build them is made so that they everyone sort of reaches a limit. Like, not everyone's supposed to finish everything. Everyone's going to reach a limit, and as you can see from the marking scheme, you can hit your limit around stage 1, stage 2, and be like, oh, this is fine, I've already passed, so it's not too bad. Yeah, and also, like, it's hump week in hump term of the year. It's like halfway through the academic year, so I think this is the point where we're at our most tired, so it can be difficult. If you want to check out one of the streams that I've got recorded, I haven't actually copied the video across to Moodle and Echo 360 yet, but there's a video on professionalism, and that might actually be a nice one to watch, because I don't just talk about professionalism. I talk about what it means to survive the work that you're doing, and that might help if you're thinking about burnout and stuff like that. People talking about marching blocks and Gravity Storm. I'm not going to talk too much about it, because there are still some people with extensions working on the assignment, so I'm definitely not going to talk solutions or anything. I think they're difficult in different ways, those ones. And people are saying, yeah, ran out of time because you're working on other assignments and stuff. Yeah, I think that's totally fine. Like, finishing all the stages was never a full intention. I tried to make that clear in the beginning, that it wasn't something that everyone had to do. I'm just looking in chat. People are talking about how they're working on style and other things like that. Yeah. Matthew's asking about a reaction video to the to the YouTube video. That would actually be really funny if I watched the YouTube video of someone else just picking apart my assignment and then do a reaction video to it. I'd be like, nope, that's not how I would solve that or something. That would actually be really interesting if they do solve it in a really weird or unorthodox way, and then it'll be really obvious if anyone used it or not. Anyway, shout out to Dean for the assignment help. That's cool. And people were saying the tutors were awesome. I'm glad that you got a lot of good help from people. Okay. Alright, that's enough from chat there. Okay, so let's get into the content we're going to talk about today. So we've now put together a fair bit of content. We've started to learn about things like pointers and structs and stuff like that. What I'm going to do today is start with a reasonable sort of recap of what we've done with pointers and functions and memory. And then we're going to look at actually manually managing our own memory. So, last lecture, we were looking at characters and strings. That is, using letters and using arrays of letters to be words and or lines of text. If you've had your tutorial already this week, not that many people, but during this tutorial this week, we're going to work on that a fair bit. So we've got a whole bunch of exercises that are based on using words. It's a fun little lab this time because it's entirely based on cryptography. So cryptography is the field of taking text information and then turning it into something that is unreadable but can be deciphered if you've got the right information. So we're doing some of the simple ones, some of the ones that were set up thousands of years ago, the Roman, what they call the Caesar cipher and stuff. So that might be fun if people are interested in that kind of thing. Even if you're not interested in that kind of thing, you'll learn a bit about using strings there. So I think that's important for us to cement that. We also talked about structs. We didn't really go deep on structs. We are going to go a bit deeper on structs. I'm going to recap them a little bit. We're not going to be writing any code today, but on Thursday we'll be writing some code, and in that we're going to definitely be using some structs. So I'm not going to talk too much about it on this slide, actually, because I've got some slides that's going to recap some of this stuff. But today, what we're going to look at is two concepts that are going to build up information for us in the future. The first one is direct use of memory. So we're going to look at actually saying, I would like a piece of memory from the computer. So I want to use a piece of memory to store some information. And it's going to be different from the way that we've been grabbing memory up until now. So up until now, we've been sort of grabbing a piece of memory to use by saying, I have a variable. And when you ask for a variable, you just get given a piece of memory. Every variable that we'll create sits inside curly brackets, and at the end of the curly brackets, it gets given back to the computer. But now we're going to have situations where we can say, okay, when the curly brackets end, we want that memory to stick around because we've got another reason to use it. We're going to keep variables outside of functions and other things like that. So slightly more complex use of things, and us sort of actively claiming the memory for use. So we're going to look at the way that we put that together. This is kind of, we're getting to sort of deep dive territory, stuff that you're only going to see in a language that's like C, rather than languages like Python and Java and stuff like that don't have this kind of concept. What we would consider is what we're diving into now is getting one step closer to the computer. I had a friend who's like, this is a slightly idiotic thing. It makes no difference, but used to take their shoes off when they drove because it would be like one step closer to the vehicle, and it was just like that's a preposterous idea. But you know, do whatever you want to. I think there's actually a ruling on that where you're specifically not supposed to do that because people will not hit the brakes as hard in bare feet as if they're wearing a shoe. So I think that might actually have legal implications. I don't know, this was years ago, so I'm not gonna let's chase them down and send the police after them. No, we're not gonna do that. But this in C, this is actually us getting one step closer to the machine. In a lot of other programming languages, we won't necessarily be doing this, but this is to really get you an understanding of like what it means to use memory, to grab a piece of memory, use it, have it last longer than the curly brackets that it's in, the scope that it's in, and then be able to give it back later. So we're going to look at that today. We're also going to look at multi-file projects. We're looking at the idea that up until now, all of our projects have been in a single C file. So it's just like program.c, freefall.c, lab1.c, you know, all that kind of stuff. But we've hinted at the idea that there are multiple files around. Because every time we did a hash include, I was saying, okay, there's another file somewhere. C owns another file, this H file, and we can grab stuff from that H file and we can use it in our C file. So we're going to start to look at the idea that you could actually write multiple files yourself and include them in each other, and then we could separate our content into multiple files based on the purpose that they are, and then be able to use them together. We're going to look at a specific way that this works because C has a specific way of doing this, and it's going to be, I hope it'll be interesting, because like what this is going to do is it's going to make a whole bunch of things more clear as to why we were doing things like function definitions and declarations separately and things like that. So a lot of interesting stuff. I mean, this is what we do, right? I tell you something and I say, don't worry about this later on. I'm going to tell you why this thing is as it is. So I always ask you to trust me when I'm teaching you something, where I say, look, I'm just going to do it this way, and I know that you want to do it different ways. I know that it doesn't seem to make sense why we're doing it this way, but we'll see why later. So a lot of the stuff about why we were putting functions like they are becomes more clear once we do multi-file projects. We're going to go deeper into this. You're actually never in 1511 going to be expected to build your own multi-file project. It's complex enough that it's a bit fiddly to be able to understand and use it. So we're going to build most of them for you, give you a bit of familiarity with it, and you'll start to build your own in later subjects. What are people saying there? Johnny Zhang says that I shouldn't wear clothes while coding. Look, I'm not gonna tell you how to live your life in your own home. I think some people wear gloves while coding, and it's like the opposite. It's like you're not actually closer to the machine, but you're cooler because you're wearing gloves. And Andrew's laughing at the shoes off thing and saying hug the computer while coding. So Liang says, can I close my window? Sounds like I'm lecturing for a moving car because of the wind. The window is actually shut, but what I'm going to do is close my blinds and drop my curtains here. So now there's something insulating us from the noise. We'll see if that gets better. I mean, the noise is kind of like rocking this whole room that I'm in right now, but we'll see how it's going. Okay, so let's do a recap because we've had a week off. So since we've had a week off, I fully expect everyone to have completely forgotten everything in the entire subject, apart from freefall, which may have been the only thing that you were doing in your time off. Liang and Masony, I'm not sure whether it's the mic or the window, but there's definitely heaps of wind outside. Like, I can hear it clearly coming off the windows, but now I've put a heavy curtain down and closed the blinds, so I can still hear the wind a little bit, but hopefully it's not too bad. Yeah, it's raining pretty heavily everywhere we are now. Taylor's laughing at me saying everyone's forgotten everything. Okay, so let's recap pointers and structs and things, because I think this is important. Okay, a pointer. Concept of the pointer, let's remember this. Pointer is a variable. It stores a memory address. If we want to find the address of any variable, we can use AND to say, okay, where is this variable? So if I say AND of this variable I, it tells us where in memory this I is stored, because every variable is stored in a piece of memory somewhere. To create a pointer, we use the star, and we also use the star when we're accessing a pointer. This star access of the pointer says, I don't want to know the address that the pointer aims at, but I want to follow this pointer to the address and say, what's the value of the variable the pointer is aimed at? So this is a matter of practice, getting a handle on the difference between the star and the and how to use it, and also the arrow, which is something that we use. I've got slides for that. I'll talk about that in a second. A quick recap on structs. So if you need detailed information about how structs work, I suggest the video for the Tuesday in week 6, or the actual time I introduced it was the Thursday in week 5, which is where you get the theory, and I did an example using structs during week 6. You don't need it. It's pretty important that everything that I did in week 6 is optional content. It's not none of the theory. I didn't introduce any new theory in week 6, but I just went through some things. So week 6, the one of the lectures that I did was just sort of to do a little bit of work based on everything that we've learned so far, and I did that with this this struct here that was based on benders. I took it from the fact that last year, third term, I think, I was rewatching Avatar: The Last Airbender, and so I did this thing based on the characters from that. So if you're a fan of Avatar, you can watch my little homage to that if you like. So structs are our ability to create our own variable types. So after doing this thing called struct bender, I now have a new variable type called struct bender, and it's made up of a name of a certain length. I'm going to assume there's a hash define somewhere else for this. The sample code I've got, if you want to look at that, it does obviously has the hash define. An element that they use, the amount of power they have, and the amount of health they have. So I made these go in like this simulated kind of computer game style fight. When we're using pointers and structs together, and now I haven't talked about this that much, but I have a little bit, we're going to start using this more. If I have a pointer to something, so this bender is called person, and I want to say just print out stuff, I can, if I want to, say follow the pointer to this struct into the struct and grab one of the fields inside. So the person's name, so I know that there is a field inside called name, and so if I have a pointer to the struct and I'm looking inside, then I can use the arrow, and the arrow will say, okay, follow the pointer to the struct, look at one of the fields inside the struct and get its information. So the way I like to think about it is, if my access to the struct is pointy, because it's a pointer to a struct, that's the star there, I use the pointy connector. Otherwise, if I just have access to the struct itself, not a pointer to it, then I can use the dot to access the fields inside it. I wonder if we showed the dot. Oh, we haven't showed the dot. Yeah. Okay, so that's a quick recap about what's going on there. Oh, James is asking if structs go in or outside a function, inside or outside the main. They go outside the main. There's something that exists for the entirety of our program, so not just the main, but other functions might need to know about it, so it goes outside. James is also asking, do you need a declaration at the start like a function? Yes. So the structs do need to be declared before anything uses them. So generally what we'll do is we'll do our includes and our hash defines, we'll declare our structs, we'll declare our functions, and then we'll start running our code in our main. Not running, but that's where we'll put our code. So we'll see a bit of that structure. If you want to, you can check out the thing that I did in week 6. Otherwise, I'm going to do stuff with structs I was about to say tomorrow, on Thursday. And then you'll see me using structs there, and the layout will be the same. I actually have something with structs that I'm going to show today. We're not going to write it, but I'm going to show it today with a multi-file project, and that actually has the same layout for structs. Reese is saying there was a huge argument about the lore in Avatar. I think it's there are enough ambiguous things that it's kind of fun to see what's happening. Shayek's saying, so structs are a global variable. No, I wouldn't necessarily say that. I think Dean's going to explain it. I'm going to let Dean explain that in text while I go on to other things here. Okay, so now we're moving on to new things. Well, not actually new things, but I want to go back again and look at functions and how they work with memory, because this is going to be important for how we use memory. So, what gets given to a function? When we have a function and the function has variables in it, anything that we put into the function has its values copied into those variables. Any input variables in a function are created as completely new variables when the function starts running. So, the function has its own set of curly brackets and its own variables. They're just before the curly brackets, but they will basically get created when the function is called, based on whatever values get given to it. The function will then have its own set of variables that it will use. So when we have a function like this function is called doubler, and you should be careful with a function like this, because this function is functionally try to not use the keywords too much when I'm talking about this, right? This function is not really going to do anything, because if I pass a number into this function, it's going to create a new variable called number, and it's going to double it. So it's going to double number, but it is not going to double the variable it was given. So x is 5, I call doubler on x, and logically, intuitively, the way I'm thinking is like, if I call a function called doubler, I expect the thing to have doubled, but it doesn't. X remains 5, but the number that's in here did get doubled, but it had no effect on x, because x was never actually given to the function. The value 5 was given to the function. So that's one of the things that we need to remember about functions. That's one of the ways that they're going to work. The way that we use to get around this is we can give pointers to functions instead. So if I give a pointer to a function, 2 copies of a pointer leading to a variable will give us access to the one variable. So it's like me saying, I have the address of a house. I can write down a copy of the address of the house and give it to someone else. Both people can find the same place. And if anyone does anything to what's inside the house, so they change what's in there, they take something out of it, they put something new in it, stretching the metaphor here a little bit, but they can change the values in there. Both people who are looking at those pointers and looking at the variable will be able to see the changes in that variable. So this means that if I use pointers in functions, I am giving access to this variable, to this function. Whereas usually everything that's inside this function, any changes made inside this function will sort of disappear when the function finishes. Because I've got a pointer to the variable, I can change something that's outside of the function's own curly brackets. So the pointer gives me access to memory that's somewhere else. So the new example here is if I have a double function that uses a pointer. So this thing says I've been given a pointer to an integer, and everything that I'm using in here uses the star that says I'm going to follow this pointer to where it was aiming at, and I'm going to find the variable that it was aiming at. I'm going to make changes to that variable. Now, when I call this, the x variable will actually be doubled, because I've created a pointer to x, and I've named it pointer x. Makes things a little bit easier for us here. And I've said pointer x is a pointer, that's the star there, and it's pointed the address of this variable here. Now when I pass that pointer into this gives this function access to that memory location, which is where this variable was stored. So if I make changes to the stuff that's in that variable location, it'll change x. So that's one of the fundamental differences between us passing a value into a function which is the value of a variable. It just gives me the number value of the variable, or the letter value, whatever the variable happens to be storing, just gets copied into the function. But if I copy a pointer into the function, that gives me access to the same piece of memory. So subtle difference there, very important. It's the kind of thing that we're going to be using a bit. So this is the difference between passing a number around and passing the ability to access a piece of memory around. So different things. Another thing to remember is that you can tell I'm recapping a lot of the stuff that we were introducing before week 6 here. I see a lot of chat in there, but I see Dean answering a lot of chat in there, so I'm going to let Dean answer a lot of the chat while I keep talking. Arrays, the interesting thing about an array is the variable for the array. So this is if we don't put square brackets on the array and we just use it as a variable. The array will actually represent the memory address of the start of the memory where all the array's elements are. So if I have the array without the square brackets and I give that array to a function, it's very, very similar to if I gave a pointer to a function. It says, okay, here's the start of memory where the array is, and now you can access the array elements. And this is the reason why every time we've been, because we actually sneakily did this before, we'd actually told you the difference between pointer access and passing in values to functions and things like that. Every time we put an array into a function, we're able to make changes to the original array, and that was because of this kind of structure. The array is actually the array variable is actually the memory address of the first element in the array. We've got some examples here. The example actually has another function here, so we should look at this function. I'll go back. If I have a function that says double all, so I'm just going on this theme of just doubling numbers, that says, for an array of a certain length that is this array, I'm going to loop through, so this is a really basic while loop through an array, and for every number in the array, I'm going to replace it with double itself, so doubling each number in the array. And so we've built an array here, simple array that just has numbers 1, 2, 3, and double all. All of this code here is just a loop that prints out the array, so don't worry about that. Just assume that this is printing out all numbers in the array. What it's going to do is print out the numbers 2, 4, 6, because double all had access to the array, because we gave it the array without the square brackets. So if I gave it something with square brackets, that's actually just going to give it a variable value. But if I don't use the square brackets, I say, here's the whole array. Because remember, the square bracket says I only want part of the array, and this is which part I want. If I don't use the square brackets, I'm giving it the whole array. The whole array is just the address of the array. So I could give double all the address of the array here, which means it would be able to access individual elements of that array. And there's only one array. There isn't a second copy of the array called numbers in here. I mean, when you think about it, there is a second copy of the address of the array, but the actual array storage of the multiple integers only happens once here in the main, and then double all gets access to it. So let's look deeper at what's going on with our functions. When we call a function, this is what happens. So my main function's here. Let's say this is my memory for my my entire program. Obviously, none of this is to scale. It's not even organized the same way that memory would be organized. This is just drawn in a way that I hope that you will understand. When I call another function in my main, it gets its own memory. So it gets its memory created. Not to scale, it's not necessarily going to be the same size as the main function, but any variables that are declared inside the function. This includes the input variables. So this includes if the array has any inputs, they're going to be created inside this piece of memory. So the function gets, you have this chunk of memory you can work with, you can put your variables in it, and you can do all the other working and stuff in there. This gets created when the function starts getting called, and when the function finishes, this piece of memory will be given back to the system, and everything in it will be not necessarily wiped, but abandoned. So when the function ends here, we can say, okay, we hit the end of our curly brackets, or we hit the return keyword. Either one of those things said the function ends. And at that point, control of the program will go back to the function that called it, which in this case is back to the main function, and then this memory kind of disappears. I mean, disappears isn't actually the best word for it, because the memory is still there. Potentially all of our stuff in it is still there, but we can't trust it to still be there, because now that is what we consider to be free memory again. And so if I suddenly wanted to declare more variables from my main, they might start taking up this space, right? So we can't trust that any of our stuff is still there. We're going to assume that our stuff was gone. So when this function hits its curly brackets or its return statement, it will disappear. We'll go back to our main, and then everything that was in here is no longer accessible, which means anything that we create inside the function exists only for the length of time that the function exists. So we've got to be careful if we want to give something back from a function. If we've created something and we want to give it to something else, we have to be careful about how we do that. So I've got an example here. What if we did want to use a function to create some data? So we wanted to use a function that was going to actually build an array. Like, this is a trivial example here. But you can see that this is not necessarily going to work. So I have a function here that says I want to give you an integer pointer, which means I want to give you access to an integer somewhere, or a memory address for an integer. A memory address for an integer could be considered, it's not exactly, but can be considered similar to an array, because an integer pointer and array store the same kind of value, which is a memory address that aims at an integer. If I use this function here and I create this array, and I say, all right, I've got this array, I'm going to give you numbers, which is the address of the first element in this array. The address of an element of an array matches up with an integer pointer, same type, because they're memory addresses of integers. This all looks legal, you know, in terms of C. I'm saying I've created something and I'm going to give you the address of the thing that I've created. The only problem is I call this function, and then when I hit this curly bracket here and the function ends, this variable, this array that I've been created is now non-existent, because I've hit the end of the curly brackets. Oops. I've hit the end of the curly brackets and this data gets wiped. It's not useful anymore. Well, it's not, I guess it's still useful. It's not used anymore, and we don't have access to it anymore. So I have now given a pointer to something in here. So I've created something in here and I've passed a pointer back to my main. My main now has a pointer to this stuff. But this stuff, there's no guarantee that this stuff is even still there anymore. So here's an issue where at the moment, given what we know so far with C, we can't actually do something like this. We can't create something in a function, and sometimes that seems like a cool idea. You know, when we want to separate stuff into functions, and I've got, say, a function that's going to create, I don't know, a line of blocks in freefall, and those blocks are going to have their own particular stats and stuff like that, and instead of being stored in the grid, they were going to be stored elsewhere. And I wanted to do that multiple times. Or, for example, I wanted each block to be its own struct, and I wanted to create those structs and then put them into an array or something like that. It'd be really nice to have a function that could create these things, because I'm going to be doing it so many times. I want that repeated code to be able to be run multiple times. Unfortunately, with our current state of knowing about C, I can't create something in a function and expect it to exist longer than the function itself. So the answer to this now is, let's build the capability to create something that will last longer than the function that it's in. And so the answer to that is a thing called memory allocation. So memory allocation is our ability to say to our computer, give me a piece of memory and don't clean it up for me. So we consider it cleaning up, where it's like, whenever we hit a curly brackets, our program will actually go back through all of the variables that we used inside those curly brackets and say, if you were declared between these curly brackets, or you're one of the input variables for the function, we're going to now pack you up and send you away. You're no longer in use. You have, to use the technical term, you've gone out of scope. So scope is the bit that we're focusing on at any particular point in time, and scope is nearly always governed by sets of curly brackets. So we go, okay, we're in scope of this set of curly brackets at the moment. When it closes, everything inside it gets flushed away. It's no longer used. If we want to say, I want something to last longer than that, we can do that. In C, we can say, I specifically want a piece of memory, and I'm going to use it. And we're now going to use this function here called malloc. Malloc, the demon from the house. Yes, I just have to say that every time I see that word because it's funny. It's actually short for memory allocation, so it's not the name of a Book of Revelations demon or anything like that. But we have this function called malloc, and it allows us to basically ask our computer for a free chunk of memory. So we say to our computer, I need memory to store a variable. And so I say, please allocate me this much memory. So we're actually going to say how much memory we need. It's going to be an integer, and we're going to say how many bytes we need. I'm going to show you a way we're going to do this, though, because we're never going to be like counting exactly how many bytes something is and saying it. But what this does is it gives us control of a block of memory. So when we hit the curly brackets, our block of memory is not going to get cleaned up. We're going to clean it up ourselves, which is why we also have a matching function called free. So we allocate the memory, and when we say we want to free the memory, that's us saying, okay, now we know we're not going to use that particular variable again. Let me free that memory and give it back to my computer. So we have two things. We have one thing that grabs us memory that we can use, and another thing that says, okay, now we're going to give it back. So it's nearly like one of them is the creation of a variable, malloc, but we're doing it manually now, and the other one is what happens when we hit the curly brackets. So usually what happens when we hit the curly brackets is we just give back all the memory that we used. But now, if it's not automatically going to be cleaned up, so it's not going to be cleaned up by the curly brackets ending, we need to do it ourselves. We need to hit a point where we say, okay, now we don't need this thing anymore, we give it back. So basically everything we create, we're going to clean up afterwards. What was the discussion? Okay. Doesn't look like there's any questions in there that are specific to what I'm talking about right now. Okay, so let's look in a diagram, because sometimes it's really good to think about this theoretically, about what's happening here. What malloc does, so what a memory allocation can do. So when we have our main function, we've got our variables here. And then we have the function that's called by the main. It would have its own variables as well, potentially. I mean, you can do functions that have no variables at all, but very rare. When we call malloc inside a function, what that's going to do is give us another piece of memory. So this is going to be memory that's accessible to our program. So it's still limited to our program. We can't just grab memory from, you know, some other part of our computer that we're not doing anything else with. When we do that, our program gets this other piece of memory, and we say, okay, here is the memory that was given to us by malloc. We asked for a certain amount of memory. This is really, really often going to be, I want to make a struct, and I want to make a copy of a struct well, not a copy. I want to make a struct variable. So the difference between a struct, you know, when we have a struct declaration, the one that's outside the code is the one that says what kind of stuff goes into the struct. When we make an individual struct, we need to store it in memory. So what we would often do is we would malloc enough memory for that struct, and so it might be here. So we've got our variable sitting in memory here. The thing about this memory being outside of this function means that when this function ends here, so this function ends and this memory is no longer accessible, when I allocated the memory, I got told where it was. So we've built up this already. We know the mechanism for knowing where a piece of memory is. It's a pointer. So we were given this pointer here that says, okay, now we always know where this memory is. We know where this variable is because we've got this pointer. If we give this pointer back to the main, this memory is still accessible. It's not part of the memory that gets cleaned up because we manually allocated it. It doesn't actually stand for manual allocation. It stands for memory allocation, but we think of it this way. We manually created this piece of memory, which means it's not part of the automatic process of memory that just gets freed on its own. So this memory stayed after the function finished. So now we have the ability to create something in a function that lasts longer than the function itself. The downside to that is if we've created something that lasts longer than the function, we have to make sure that something remembers that this is there and cleans this up. So something else in our program has to know that this thing's still hanging around. So when we use malloc, we use this other operator called sizeof. It looks like a function, but it's not a function because it doesn't actually take normal inputs like a function. But we call it an operator, so it's a slightly different thing. Sizeof is really, really useful to us because we can plug variable types into sizeof. And when we say a variable type in here, we can actually just use the type name. And what sizeof will do is it'll look at a type name and it'll say, I know how much memory a variable of that type takes. And then it will convert that into how many bytes this would need so that when we malloc, we always get exactly the right size for that particular thing. So here, reasonably trivial, but not always an assumption. So I would say sizeof int that says if I have an integer that for the most part I'm expecting my integers to be 32 bits. So if my integer is 32 bits, I'm expecting sizeof to say 4 bytes because remember there's 8 bits in a byte. So sizeof an integer should give me the number 4. But I'm just assuming that because of our current architecture and the way we're doing things, integers are 32 bits. It's quite conceivable that an integer, depending on your compiler and the operating system and other things that you're working with, might not be 32 bits forever. There might be a point in the future where the integer is re-specified to be a different size. It could be pretty dangerous for a lot of assumptions that we've made in C, but if we use sizeof, we're kind of protected against that. So whatever C thinks an int is at that point in time, we're going to have that much memory. So if I say malloc sizeof integer, this is going to allocate me enough memory for an integer. I don't even need to know that the integer is 32 bits here. All I need to know is that I have enough memory for an integer, and malloc is going to return to me, it's going to give me the address of the memory that it has just created. So how do I store an address? I store an address in a pointer. So I create a variable, which is an integer pointer, and I allocate memory of the size of a pointer. Oh, sorry. Damn it. I had that all lined up. I allocate memory of the size of an integer. So I've got an integer amount of memory here that I've allocated. Memory allocation tells me where it is. I store where it is in this pointer. So long as I have this pointer, I now have access to an integer. But that integer exists beyond the functions that that created it. So long as I keep track of this pointer, and I could set the variable to a number. So this memory allocated variable acts exactly the same as a normal variable. Well, I shouldn't say that. It doesn't get cleaned up the same as a normal variable. But in terms of us saying what its value is, changing it, using it in maths, all that kind of stuff, we can just do that the same way as we would do any other variable we had a pointer to. We can never access it like a variable with its own name, but we can access it through its pointer. And then we can pass its pointer around to other parts of code, and now we have the capability that we didn't have before, where we tried to create a variable and have it last longer than the curly brackets that it was created in. So now this memory allocated variable that's created inside this curly brackets will not disappear when this curly bracket's finished. We can give this pointer back, which is just the address, the value of this pointer can be given outside to something else. Whatever receives that will have access to that piece of memory. So that piece of memory doesn't go away when I reach the end of this. Charles is asking if sizeof isn't a function, it's a weird keyword. Yeah, it's a super weird keyword. Think of it like this: sizeof does not take a normal input, right? So int is not a normal input. Int is a type. Usually every input to a function is a variable or a value, right? And you don't receive a type because a type is an abstract concept of something, which is why sizeof is considered an operator, not a function. I think Dean's also talking about that, yeah. I'm going to let Dean answer the questions in there. I just looked and was like, there's a lot of questions, but there's also a lot of stuff from Dean. So I think he's going to answer stuff for the moment. Okay, so the other thing that we need to do, if we go around allocating memory, we're just grabbing all these blocks of memory on our computer and we're putting values in it, we need to make sure that this is cleaned up. Because the interesting thing about this is that we've specifically said that this memory allocation lasts longer than these curly brackets. So all of the safeguards I usually have for my variables, that when we hit the curly bracket, everything else that I would have created in here will get cleaned up for me. I don't have to do anything with it. But this one is allocated outside of, like, to exist outside of this function, which means there's nothing that comes back and cleans this up. So we have to do it ourselves. We're going to write free, and sorry, not going to write it. It's a function that already exists, and we're going to use it whenever we're finished working with something. So here, I've called my malloc number function, which is this function which is going to allocate some memory. So I know that I've allocated some memory. I have a piece of memory somewhere in my system that's floating memory. It's my special manually allocated memory that I'm using. I have to make sure that I give it back. So if I don't give it back, I end up in a situation where we get what's known as a memory leak. A memory leak, it's interesting because it's not exactly what it sounds like, but a memory leak is like I've claimed a piece of memory and I haven't given it back to my computer. So it's nearly like the memory is leaking out of the computer because I've claimed it. So if I claim it and I don't do anything with it, my computer doesn't know that I'm not planning on doing something with it in the future or something like that. So what it ends up being is memory that nothing else on my computer can use. And if I was, for example, to lose access to this pointer or to change this pointer to aim somewhere else, I would lose access to that piece of memory. I don't know where it is anymore. And then it's like it's leaking out of my system because nothing can use it. And eventually you can leak all the memory out of your system if you're not careful. I mean, it's hard to do. Actually, it's not hard to do at all. I can show you how to do it. But it's the kind of thing that can bring down large C programs, especially anything that's going to be running again and again and again for a long time. So, for example, if we had a... there's someone back there. I'm not sure if she's going to come and visit today. If we had, say, a mail server, so for example, something that's going to handle a whole lot of email, that kind of thing is going to be up for a very long time. We expect those things to run for months on end without being restarted. And if this thing, every time it called a particular function, leaked one pointer worth of memory, or just one integer worth of memory, most of the time we wouldn't notice. But if you run this thing for like a week, then suddenly the computer it's running on runs out of memory and can't run any other programs, then you know that something's up. And so we can get memory leaks like that. Oh, I apologize everyone who heard chicken in the background. I think she was meowing at my partner and running off in the other direction, so you may have to wait for the usual Thursday afternoon chicken time. Speaking of completely random things like that, I think Dan Mansfield and I are going to try to do a joint stream on Friday evening, so I'll probably hop into his stream, and we might actually do it so both of our faces are on there. We'll see. We haven't organized it fully, but we'll probably do something like that. Okay. So here's a diagram, because I think all of this stuff needs diagrams to fully understand what's going on. When we have allocated memory, and so I'm not even worried about who allocated this memory, I just know that I've got allocated memory, and I've got a pointer to that memory that I've got in my main, so I know where this memory is, I've kept track of it. When I call free on this pointer, this memory then goes away. It goes away in the same way that the memory from the function went away, where it basically gets turned back into open space that I can put other things in if I want to. So we just got to remember that every piece of memory that was allocated must be freed later. And it's hard to remember this because it gets fiddly, but that's something we want to keep in our mind. Everything we allocate, we want to free. So, I'm trying to think about what else I wanted to say about this. A recap of what everything we're going to do with memory. Sizeof tells us how big something's going to be. Remember, not a function, doesn't take variables or values as input, but takes types as input, and it's going to actually like feel a little bit like a function, even though it's not. It's just going to tell you the size of something. So very, very commonly we're going to be using malloc and sizeof together. We will very, very rarely use malloc without sizeof, and we'll also very rarely use sizeof on its own because it doesn't really have a purpose on its own. But definitely when we're using malloc, the way that we're going to teach you to use it, which is the most common way to use it, is to use malloc with sizeof inside it, and then you say the type that you want to store there. Everything that we malloc, we want to free afterwards. Actually, you know what? I'm not going to go on break just yet. I think we're talking about Daniel Mansfield. Should 1v1 him in chess? I don't think I would do that well in a one-on-one against Daniel in chess. I think he might actually know how to play chess. I think I need to one-on-one him in Warhammer, because I have a feeling, like, we both kind of get into it, but I have a feeling I've played more Warhammer than him. Steve is asking a good question. Why can't the computer just know to free up all the memory used when the program finishes? Interestingly, the computer will free up all the memory the program used when it finishes. The thing that we want to do, though, is we want to free up the memory for each particular variable when we're not using it anymore. So yes, this is kind of trivial if the program's about to end, but if we're running a program that runs forever and it loops, and it's constantly doing stuff and it runs for weeks on end, we don't want that kind of thing to be leaking. And so what we're going to teach you is the entire proper way of doing things, which is we free everything that we allocate. Even if we know that the program itself is going to free all the memory we allocated when it finishes, we don't want to have these random leaks happening as our programs run. Because if we don't teach you the fundamentals of how we're going to clean up all our memory after ourselves, the first time you write a program that's like a server-side program that's going to run for a long time, if you haven't learned how to clean up all your own memory leaks, you're going to end up with something that crashes after a little while. So the longer it's been on, the likelier it is to cause a crash when it runs out of memory. Just looking at you, Windows 95. But anyway, there was so much stuff, like in those old versions of Windows. There was like this. It was like rust. Like, it was like a machine that rusted. Only how did it rust? It was rusting virtually. It was building up things like memory leaks and stuff like that. And if anyone ever played with the Windows registry, it was just building up all this random data and things. And so it would crash reliably on based on how long you'd run it, because there were actually memory leaks in it. Let me show you, because UG is asking what is the consequence of a memory leak. So one of the consequences of the memory leak is that other programs can't run. The other consequences is we might use up so much RAM on our computer that nothing else can run. So let me just hop in here to VLab. I'm gonna show you a really, really simple demo. What are we in? Lecture 11. I don't know why I just did ls on a directory that I just created. I think I do ls like out of instinct, because I know this directory is empty because I just made it. I'm going to call this memory leak.c as a joke, because this is definitely a memory leak. A demo program that will 100% leak memory. What are we in? July 2020. Okay. So, in order to use memory allocation, I'm going to use the standard library. So, the standard library is where the functions malloc and free are. I'm going to assume that I'm using standard input output. I don't even know if I definitely need it or not, because this is a toy program. There's not actually much going on here. Okay, so let's just do a really simple memory allocation. So integer pointer, I pointer, integer pointer. Yeah, there's probably going to be a better name for this than this, but considering I don't have a purpose for this, I don't have an easy way to name it. If I had a reason for it to be that pointer, then it might have a better name. So I'm going to call malloc, and in malloc I'm going to call sizeof. Note, syntax highlighting here gives it a bold red name, which is the same kind of bold that we had for if and while and things like that. Shows you that this is a C keyword. So this is another thing that we would not be able to use as a variable name. So sizeof an integer. Okay, so I can create this, and then I could use it for things. So let's just run this program. It's got nothing in it. I've just declared a variable. Let me just clear this. So I'm going to DCC memory leak. I'll just call the program leak. Okay, I'm getting a warning for an unused variable. That's fine. I know I'm not using the variable because that was a really trivial program. So I'm still going to run this. And nothing's going to happen, right? Because nothing functionally happened in this program. I didn't do any output or anything like that. All I did was do a memory allocation. However, if I want to, I can compile this with this flag called leak check. And what this is going to do is it's going to tell me if there was any memory allocated when this program finished that I forgot to free somewhere along the way. So if I do leak check on that and then run it, it will finish. But this time when it finishes, it doesn't just do nothing. It says, hey, I found something that you didn't free. Free not called for memory allocated with malloc in the function main in memoryleak.c at line 9. So it's telling me that you created some memory here in line 9 that you never freed. So leak check is something that we're going to be using a fair bit later when we start playing around with memory, because it's sort of a backup plan for us if we're not careful to free everything we malloc. So basically every time this function's called, there should be a free somewhere else. So if I say free on iPointer, what that's going to do is say this pointer is storing somewhere a memory address. And it's an integer pointer, so it's storing an integer's worth of memory somewhere. Free says go to that piece of memory and give it back to the computer. So let's save this, and I compile that with leak check and run it. And now it says, okay, you finished fine, because you did declare a variable and memory allocated, but you gave it back to the system before you cleaned up. So you used it, you cleaned up after yourself, and then you left. So that's pretty good. Dean, I was getting there. So what issue that we could get here is, what if we lost this pointer? So what I'm gonna do here, I'm going to get rid of that free because I'm not going to use that for the moment. Don't ever do this. In general, don't do this. It's a bad idea. While 1 is a bad idea. I have no way out of this loop. But don't worry. I've got a backup plan for how I get out of this loop. Now, this isn't even a he's behind you moment. He's behind you. This is much worse than a he's behind you moment. What I'm doing is I'm allocating memory in a pointer that's inside curly brackets, which means that this pointer will disappear the second I hit this curly bracket, which is right after I created it. Which means I am now allocating memory that I will lose immediately. So I will lose access to this memory immediately because I'm not saving any of these pointers anywhere. And I've got this in a while 1, which is a loop that will never end, so this will go forever. So I'm going to save this and compile this. Basically what you're doing is you're watching someone just go, okay, so here I have a bomb, and now I am taping this bomb to my head. But I'm doing it with my computer, not me, so it's a bit safer. So, what I'm now doing is I'm allocating a small piece of memory, no big deal. Then I'm putting it inside a loop, so it gets allocated multiple times. Let me set up some stuff before we do this. I'm going to run this command. The command I ran there was called top. Top is, if you've done stuff like working in Windows, you would have seen something like a performance. Was it a resource manager or performance manager and stuff like that, where you can see what programs are running on your computer and what they're doing. So here we've got the percentage of memory that something's using, how much time it's been running for, top has been running for 13 seconds, how much CPU it's using and stuff like that. So this is us being able to see. This will be really funny if I get an email from SS later today just going, Mark, what have you been doing? Because you managed to use all of the memory on one of the VLab machines. Anyway. So don't everyone do this at once. That would be pretty funny if we all ran this code at the same time on the same VLab machines. Anyway, let's compile this and run this. But what I want to do is I want to show you what's happening when I run this, right? Okay. Perfectly fine program. Okay, we're getting the same warning for unused variable. This is because this variable is most definitely not being used. All I did was create this pointer and never did anything with it. So that warning is a useful one to know about when you're in a program where you want it to do something. So this program's really not doing anything. Actually didn't even need the standard input output. Okay, moment of truth. Let's run this. Okay, it's running. It's looping forever. I can't tell what's going on here, but let's come across this terminal. Leak is now running 100% of my CPU. It's using 1% of my memory. Oh wait, that's 6 gigs of memory. There's a G there. 7 gigs of memory. Oh, it has disappeared. I told you I had a backup plan for this. Killed. Press F for respect. Sorry, it was Task Manager that I was talking about. Yeah, I saw that there. At least we're working in a safe enough system where this thing grabbed 8 gigabytes of memory and the operating system said, look buddy, you've had enough to drink, go home. So, I love the chat at the moment. Did Mark say do all of this together at the same time? Memory was climbing, yes, and we're pressing F for respect because the program was killed at this point. So, let's have a closer look at what happened there. I created a very small amount of memory, but I lost access to that memory and I kept doing it. So this is not necessarily the speed at which you might leak memory, but if you do leak memory, this is the consequences eventually, is that your program will be unceremoniously dumped out of running. So when it reaches a point where it's leaked so much memory, that leaked 8 gigabytes of memory in, how long did that take me? Like 15 seconds at most. So the CPU was just running every time, allocate memory, allocate memory, allocate memory, in that while loop until it used so much memory the computer said, look, you've had your limit. I was never going to give a single program on this VLAB computer more than 8 gigabytes at a time. And you used your 8 gigabytes and it's over now. So that's it. So we have just removed your program from the list of things that it's running. And that memory has been given back to the system, so I haven't destroyed something on one of your VLAB machines or anything like that. So our operating systems are safe enough that they can do that. If you can find an old enough operating system, you can actually really break stuff with this, because the older operating systems don't stop at 8 gigs; they'll just let you keep going. So you can just keep allocating memory until the operating system itself is no longer given any free memory to run things in, and it starts to grind to a halt. So this is a nice safety feature that we've got. In general, you just want to run stuff with leak check, and your stuff will end gracefully on its own, and then you'll be able to know if you're not freeing something. But this is a very extreme example of what happens if we just build up a lot of memory. Louis Hang's saying, why did it just say the one word killed? Yeah, it would be probably better if this would actually tell us why. So it would be, I think this would be a much better error message if it said, program has exceeded memory limitations or something like that. This is exactly that kind of thing when I talk about, like, if you are going to put error messages in your code, something like this is not very useful. Yes, I'm pretty sure the program's not running anymore because the prompt came back up. So I kind of know that it's been killed. But I don't know whether it crashed or it returned properly. So at least it's a little bit of information. But I would love it if this said, program has exceeded 8 gigabytes of allocated memory. This is beyond what is allowed for a single program, something like that. Yeah. People are saying it sounds like I'm in a hurricane. It does actually sound. I can't actually seal it off any more than that. I've got a heavy curtain between my my webcam and the window, but obviously, like, you can still hear it. I can hear it in the room, so I don't think there's any way I can make this better. One day I will build a soundproof studio. Ironically, there is a recording studio. Well, not really a recording studio, but it's like a small streaming room in CSE. But I don't really want to work on campus during a lockdown, so I'm going to stay at home where I know that it's only my germs here. It's not other people's as well. Okay, so having killed that, let's take a quick break because I'm a little bit over time. I think there's the stuff that I needed to talk about at the beginning, so I think it was important that I talked about issues with doing your own work and trying to learn things properly. So I think that was time well spent. But I'm a little over time at the moment, so I'm going to take a really quick break. I see 10:23 on my clock at the moment, so I'm going to take a really quick 2-minute break, come back 10:25, and then we'll move on to the next topic that I wanted to talk about today. I found a friend. So I went and found where she was, and then she meowed at me and came and said hello. So I figured I would let her say hello to you. So there's a little dose of chicken for the day. It is the morning though, so this is the time of the day where she's usually pretty lazy and napping. But she did meow and say hello and came up and walked up to me when I approached her. So she's pretty friendly. She's just hopped back off there, so we'll see where she ends up. Yeah, Charles, she does look asleep. Having said that, she wasn't napping. Usually this time of the day, she'll just be in bed. She'll just be like, I'm not getting out of bed. I mean, gotta be honest, this time of the day, I might be as well. Although it is 10:30, but, you know. Okay, so we were talking about leak checks. Oh, I didn't actually show my break slide. Ooh, I've got way too many things open at the moment. Okay, because when I've got memes, I should have memes. Actually, I'm just going to move myself out of the way. There's my, Quoty's asking if Chicken knows how to code, of course. As far as, I think that the narrative for this course was that Chicken invented C. Chicken's a little bit younger than C, but we're going to say it anyway. Chicken invented coding. So, I just love this bit. It's like, I have no memory of this memory allocation. This is something that's going to happen to you. It happens to everyone. Is that at some point your program is leaking memory and you don't know where it came from. So, usually the way around this is to be reasonably diligent with how you allocate and free memory. Is that knowing that every allocation needs a free. So every time you create something, you need to remove it when you're finished. But it's easy to forget what you've allocated, especially when you're putting allocation into different functions, and you've got a function that allocates things that's going to get called a lot. You need to figure out when you want to free it later. A deeper level of this in other programming languages is sometimes we have ways of tracking the memory that we've allocated, so that at any point we can kind of, not exactly, but we can kind of look at the memory that we've allocated and see which bits need to be freed, which bits don't. Different programming languages that are the ones that followed on from C do some of this automatically. So they try to look for memory that they think that you're not going to use again, and then they free it. They've got to be careful with this. Obviously, you don't want to free something that someone might still be using. But the situation I did there, where I just created this allocated memory again and again and again, and then it just ended up using all the available memory. Harder to do in other programming languages. So there are safety nets as you go deeper into programming, but in this beginning, when we're trying to teach you about how it works, I prefer to kind of do this in a way where it's like, no, I'm just going to give you a lot of control here, so you get to make mistakes in the environment where you're learning about it, and you can kind of see the difference between allocating memory properly, freeing it properly, and things like that. And as you saw there, what I did, nothing really happened to me there. So my computer was able to use far too much memory, and I got away with it. So, well, unless there's an email from system support in my inbox right now, but I very much doubt it, because it's not like I haven't done this before. Well, I think someone's yelling at my partner to get taken into the other room. Anyway, so that's what I'm going to talk about memory for the moment. This is not going to be super relevant yet until we start actually using it on things, but I do want you to know about it. So on Thursday, we're going to actually start using this. People asking about what was happening there. I think Dean's answering the questions there, so that's good. Okay, so let's go on to another thing that I wanted to talk about today. This is going to be a little bit compressed, so I'm going to try to fit this in half an hour. C projects with multiple files. So sometimes we're going to separate things into multiple files. This might make our readability much nicer because the bigger a single file gets, the harder it is to keep track of where you are in it or what's in that file. So we've been using hash include before. We've been using hash include for stuff like the standard libraries. But now what we want to add is the capability to hash include our own files. So we can create our own files and include them, and that's a way of us separating things into different files. And this is not just going to be a sort of random code is in different places and we're going to hash include it to kind of stitch a big code file together out of smaller ones. I mean, functionally that's what we're doing, but we're going to be better about it than that. We're going to have a specific structure for doing these things that allows us to kind of interface into other parts of things. This is what we're doing with our libraries. When we learn to do it with our own C code, it's also quite powerful and can help us out. So the reason why we would often do this is I could create a piece of code that has a whole bunch of useful kind of maybe array functions in it, and it's something that I would use again and again, and it was something I would be able to use in every program that I was using that had arrays. I could have this thing, I could build my own library in the same way that we're going to reuse standard input output in everything that we do. If I had something that was an array library that would always be able to tell me certain information about arrays, then I could just go, I'd never need to rewrite these while loops and things like this. You obviously, like, I'm obviously asking you to write these loops all the time because your goal is to practice these things as opposed to have these things ready-made that you already know how to use. But a library often works like that for us. We have these ready-made things that we reuse instead of having to rewrite them. You can think of it as like an experienced trade person walking around with a toolbox. As they learn about what they do, they learn how to use tools. They put these tools in their toolbox, and the toolbox is like a library. It's the other way around. The library is like a toolbox that you carry around with you, and instead of having to figure out what to do on the spot, you go back to your toolbox and you go, oh, this tool does this for me. And so a lot of people, a lot of experienced programmers will carry around a set of libraries with them that they use so they don't have to rewrite things. So that's what these sub-projects are. So sometimes they're reusable, sometimes they're separated just for purpose. So it's like, this library does this thing, this library does this thing. They're not necessarily more reusable than each other or anything like that, but they might be like, this one's for input and output to the terminal. This one over here is for memory management. This one is for floating point arithmetic. I'm actually referring to specific C libraries when I say that. So they're separated by purpose so that you don't have to grab things that aren't things that you need. Because, I mean, you could make an argument to say that why are we including standard input output? Why are we including standard library? Why are we including string or characters and stuff like that? Why are we including them separately? Why don't we just have a hash include all of C and use it? And that's because we don't necessarily want all of it at once. Our programs might end up really big all the time if we do that. And so what we do is we just take small chunks of it and we go, okay, this is going to minimize the stuff that we need at any particular time. Reese is saying, for the decryption lab, could we just hash include encryption and just change the array? So if you had a library that you'd written that was an encryption library, then that's definitely something that would work really well for that. I don't necessarily suggest that at this point in the labs because we haven't actually taught you that much about it yet. Yeah, give me a second. You can hear in the background somebody's getting a bit frantic. I'm going to open the door for it. I took her out of the spots that she liked, so she was getting very, very angry with me. Okay, so what we end up with, and you will have noticed this because every time we hash include, we've been hash including files with a .h on the end. And you may have noticed that none of the files that we have written for any of our labs or anything like that have been .h. They've all been .c. So there's been a completely different thing going on between the .h and the .c. And so what I want to do is explain how this works. So I've got some demo code. I should actually just... I'll do that in a second. I'll download the demo code if I have time. The .h and the .c have different purposes. So the header file will show us the capabilities of the file, and they will give us... It's nearly like the header file is a human readable file, where the C file is not necessarily. I mean, we're going to make it as human readable as we can, but it won't be as readable. So these pairs usually go together. They usually have the same name. So I would have, let's say we were talking about an encryption library, so I could have encryption.c and encryption.h. And what I would do is, if I wanted to use my encryption library, I would include the header for it, and the header would tell me all the functions that are in the library, but it wouldn't necessarily have any of the running code. The running code would be in the C file, and the header file would have just declarations. So it could declare structs, and it could declare the function prototypes, but not the entire definition of the function. And so now you're seeing, I was saying before that we're going to see a bit of the reasons why we would be using, why we would declare functions at the top of the file and then have the implementations of the functions down at the bottom of the file. This is us actually doing the header file C file thing. So these two chunks with our functions we could pull out into separate files, and we'd include the header file at the top, which would give us access to things, and the C file never actually gets included. It just gets compiled along with the code. So I think I've already kind of spoken a bit about this. The header file shows us what functionality that library or that set of files were created are going to have, and it also will often have this thing called type def, which is a type define, which is our way of creating a C type out of another type. All this actually is actually the keyword here. You can see the keyword saying define. It's not the same, but it's actually reasonably similar to the hash define. The hash define that we use was just a pure text replacement. The type def says that if I give you either one of these two words, they mean the same thing. So it's very similar to the hash define, but not exactly the same, because this is like within C, this construct that says that these two types are now the same type. So it's a way that I can uncomplicate a more complex type somewhere else. I'll show you the example before we go too deep into this, because I think that it's easier to see this in the example once I've talked about it. What we can do with this is really interesting, is we can have a struct somewhere, and we can give people access to the idea that the struct exists without actually giving them access to the code that's inside the struct. I'm going to go over this in great detail later on in term, so we'll see how this actually works later. But the interesting thing is, what I can say to people is, there exists a struct somewhere. You're going to use that struct, you don't know what's inside it. The only things you can do with this struct are call functions on it. So you can't see inside it, but you can call functions that can do things. And me saying you can't see inside it means you can't change anything inside it. So what we do sometimes with this, the header and the C file combo, is we protect against being able to see things, so that people can't accidentally change data they shouldn't be able to change. Let me just gonna have to pop open Firefox here. Where are we? We are in week 7. So I'm gonna download this project into lecture 11. Oops. I think I just set it open with instead of save. Download, save. Okay. Alright. Back across to... I didn't mean to open a new terminal there. Back across to our terminal here. If I do ls, I have my memory leak stuff there, but now I have this thing called a main.c, a person.c, and a person.h. Let's open them. I don't need this anymore. Let's open them here in gedit. We'll close that without saving. Main.c, person.c, and person.h. I don't know if you've seen this. Gedit is actually able to open multiple files at once if you do this. So here's our multi-file projects. Our first look at it. So this one's actually based on maybe in the first or second time I taught COMP1511, where I did the structs example that we do now with Avatar, because after I rewatched Avatar, I rewrote that one. First time I did it was Ninja Turtles, and then someone like drew a bat symbol in chalk on one of the boards behind me before one of the lectures, and specifically requested that I use Batman for the next example. So this example has a lot of Batman stuff in it. So the H file is going to show us some information. So it's person.h and person.c. So the purpose of this was for us to create a person and then be able to display them and give them powers and things. So you notice that in my main file, I love this one. These are the important powers that Batman has. So our H file here has some hash defines, and a header file is often going to look a lot like this. There's a lot of blue text saying what something is, and then I've just scrolled to the end of the code file here. There's not really much code. There's these declarations of functions, but there's no information about how they run. The information of how they run is here in the C file, and each of these in the C file here, I probably should have put some comments in this code here, is linked up with one of these. So when we actually compile these are going to connect together. But for the moment, what we get is our main file is going to include just the H file and not the C file. And so the only things it's going to see is these things here. So the type def is the thing I was talking about that says there's a thing which is a struct person pointer, but we're going to rename that capital P person so that when we're using it in our main, we're going to think of this thing as if it's a variable type that we've created. And the person.c and person.h file are the things that define what we can do with capital P person. So as I said here, we can create a person, which then returns the person. We can then free the person. So this is our allocating memory, and then freeing memory is in these two functions. And then we have this, we can give the person a power, and we can display what the person has. So if we were to dive into this, we would see the code that we'd actually use to make these things happen. But you don't need to know what that code is to use this. All we can do is we can say, okay, there's a way to create it, way to free it afterwards, way to give them powers, and then display. And so you can see here me using this. I can create a person, display them, give them powers, and then display them afterwards. When I'm finished, I can free them. I can use this without knowing how the code works. Exactly the same way that you use scanf, printf, without ever, some people definitely, including myself, because I haven't looked at it in years, are using this without looking at the code, right? And so in the same way, we can use this stuff in the person H without knowing what's in person C. If we want to do a deep dive into this and find out how these things work, we can look at them. So let's look at this create person here. Also, let's look at the fact that the struct is in here. we do not know what the struct is from the H file, which means our main file, which has included only the H file, does not know what the struct is. So the struct is in here. Since my main file doesn't know what the struct is, it means it cannot make changes to the struct, which means it can't accidentally change the name. And also, interestingly, it can't look in the Batman struct and figure out whether its name's actually Bruce Wayne or not. I don't know if that's actually the case. No, I think we created with the name Batman anyway. But the cool thing about this is that this struct is kind of safe behind this type definition, because we can see everything that's in this file. We can't see anything that's in this file, but we can call these functions. So our access to this struct here is actually a little indirect, because I can call this function. This function will run because I can call it from here. It will make whatever changes are necessary to make something happen, but I, in my main file, don't get to access the fields inside the struct and make changes to them. So it's kind of like, in this interface into the person, I have a wall that says you can't get through this and access these things. But there's a little window in the wall that says, okay, these are the things that you can do. You can ask me for certain things. You can ask me to create a person. I can do that. You can ask me to free the person. You ask me to give them powers. But you cannot go in and change the powers yourself. You know, you can only give them a power or display. Right? So once we've given someone a power in this, we can't take it away. And that's what happens when you create superheroes. You know, could be dangerous. Let me go back to the slide, since I've given you this like brief overview of looking at this code. I'm dumping a lot of code on you at once, actually. So I want to explain a little bit about what's going on there. So the type def means we can't see the struct, which keeps the data safe from accidentally being changed in the main. There are function declarations, but there's no definitions. So we know that the functions exist, and we can call the functions. We've seen this kind of thing before, right? Because any of the other files that I've used before that had functions in them, we could see the functions because the function declarations were before our main. And in our main, when we were calling the functions, we didn't actually necessarily have access yet to the code itself. That gets linked up later. So this was our simulation of how we would include an H file and have the C file separate. Generally, in the H file, we'll also have all the human readable stuff that describes how things work. We'd usually have comments still in the C file. Like, that C file there is probably a bit messy. I should change that. So the C file has all the hidden stuff. This is like, I always liken this, I keep using driving analogies, so I don't know if everyone drives cars or not, but this is the idea that inside a car, when I'm driving it, I've got the steering wheel and I've got the pedals that can do things, right? When I turn the steering wheel to the right, I assume that the car is going to go to the right. That means I've looked at the interface, the H file, and I said there's a function for turning right, there's a function for turning left. That's the turning the steering wheel. When I'm driving the car, I don't know why that's happening. I have an inclination that somewhere through the steering wheel, there's a mechanical connection to some power steering thing that makes the actual wheels turn in the car. Sure. I don't know exactly how that works. I just trust that it does. That's what it means to look at the H file and use it. If I was to pop the car open, have a really close look at it, probably need to be a mechanical engineer as well. I don't really know how any of that works, or at least a mechanic. I could then go into the C file and see how this works. So the C file is like popping the hood and seeing how the engine works. Well, not just the engine, just everything that's hidden from it. So you can see the difference. The H file gives us the ability to do things, and the C file says, okay, this is exactly how these things are done. So this is how we're separating these things. The main C is usually where the code starts from. Every C project, no matter how many files are in the C project, whenever we compile a C project, it must always have exactly one main function. It cannot have more than one main function, and it cannot have 0 main functions, because when we compile a program with the intention of running it, the main function is always the thing that runs first. So the main function will run, and it will grab functions from the other files and try to run them. So if I look in this, I have a main function here. In my main.c, that is a polite way to name the file that has your main function in it. Because otherwise, if you have like 18 files and you haven't told someone where the program actually starts, it's really, really hard for them to actually understand where that's going to be. So the person.h file does not have a main function in it, so we know that's not where the thing's going to start. Person.c file, no, does not have a main function in it. It just has these definitions of these other functions. So the C file is very similar to the chunk of functions that might be in, say, your freefall code that are underneath your main. So this is just like these free-floating functions that are available so long as someone knows, by including the H file, they know the declarations of these functions so they can call them. This is where the stuff is that actually runs them. So we can see here a little bit of memory allocation going there for the person, that kind of thing, but it also has the setup where it copies the name in and things like that. So what we're getting here is if you want to create a person, you can't just malloc them yourself. What you get is, if you're going to create a person, we require you to also give them a name to begin with so that we can use them. So we can say that like these functions allow you to do certain things, but they also make sure that these things work in a particular way. Right. When we're compiling something that has multiple files, this is an interesting thing, right? So the header files and the C files work very differently. Header files are always included in other things. C files are never included. C files are always compiled. Header files are never compiled. So, well, I don't want to say never compiled, but they're never part of the compile command. So, because the header files are going to be connected to the C files with #include, they're never going to be part of the compile. So, the compile command, actually I won't, this is the demo of that. I'm going to talk about that in a second. Let's actually compile it. So we're here. So, the project that I'm working on, I should probably just remove the memory leak stuff for the moment. I'm not going to keep the memory leak program because I don't really need to. I'm going to put a star on the end there, which is going to delete both this file and that file. Okay, so now it's clean. We've just got our project here that has main.c, person.c, and person.h. If I want to compile this program, first thing I want to do is make sure that there's only one main function in it. And I've had a look through, and I know there's only one main function in the main.c file. The other thing I'm going to do, if I'm going to DCC this, so DCC is going to take in a code file. Usually it would take in a code file like main.c. If I have multiple C files, I am going to compile multiple C files. I'm not going to compile the H file. It is not necessary for that to be put in as part of my compilation. If I'm going to use the functions in person.h, I need to include them somewhere. So in a sense, the code for person.h is going to get compiled as part of main.c, but if I didn't include it, it wouldn't get compiled. This is exactly the same as, for example, me not having to write something like standard input output.h to be part of what I'm compiling, because the #include function already grabs it. So if I've included person.h to use, then I don't need to actually put it in as stuff that's going to compile. But if I need the functions in person.h to run, I need person.c to get compiled. So somewhere, everything that's in person.c is going to get transformed into code that can run. And it's all actually going to get bundled into a single file. So, what would I call this program? person demo. So the interesting thing is, these two C files are not going to compile into separate files. They're all going to compile together into this one file called person demo. And person demo is going to run whatever is in the main, and it's going to have access to the things that are in person.c, all of the running function code, via the fact that main.c knows the definitions of those functions using person.h. So I do person demo like this, and I run person demo. It's going to do the following. So let's go back to our code here and have a look at what it's going to do. First thing it's going to do is going to create a person and display the person Batman. So that's Batman doesn't have any powers yet. So that's the point at which, spoiler alert, someone decides, actually I'm not even going to spoil it, someone decides that they want to become Batman, but they haven't learnt anything yet. They haven't learnt what they're actually going to do as Batman, so they go Batman with no powers. And then we give Batman the powers necessary to become the superhero the Batman becomes. So first we teach Batman ninjutsu, then we give Batman a whole bunch of technological gadgets, and then we make sure the Batman is brooding, because if you're not brooding, you're not a superhero. You can't sit on a gargoyle and not brood. And then the most important thing is we give Batman a gravelly Christian Bale voice so they can intimidate his enemies. After we've done that, we're then going to display Batman, and here we have the display of now the fully superpowered Batman. What this has done, person.h allows me to see what functions I could use. So each of those functions in there is a function I could see in person.h. I have then given these functions the correct information to be able to run. Main.c does not actually see person.c, but person.h is able to link up to these functions that have the same name. So every time I call one of those functions, it is able to run all of this stuff because they were compiled together. It's able to run this. But my main.c only knows that these functions exist, and they don't necessarily know all the nitty-gritty of how they work. So we've got this beginning. So don't worry if you don't get this fully, right? I'm dumping a lot on you right now. But what we're beginning to see is this capability that we have to provide functionality into one file from these other files. This is exactly the same as us doing #include standard io.h. I have given us these functions that have specific inputs and outputs that I can use here, and I don't necessarily know what they are. So I can't necessarily see the code. So if I was to #include standard input output.h, note the difference. Double quotes says this is my file. This is a file that's in the same directory. Angle brackets say this is a file that your compiler should know about. So when the compiler runs things, I want to use a C standard library, it's in the brackets. If I want to use a file I created myself, it's in quotes because it'll look for it. And we can actually even do things like /libraries/ we could actually have things like this that says, alright, this is pretty specific. We're going into a directory layout here, and we're looking for things in specific places, so we can organize these things if we want to. We're not going to bother with that for now. Like, we're going to do simple things where everything's in the same folder. I'm going to save that again. So if I was going to include standard input output, I would have the same kind of situation as person.h. I would see that there are functions that I could use. I wouldn't necessarily see the code and the details for them. Interestingly, note that I am not including standard input output, but I am getting stuff printed out. Now let's look at how that's working, because I don't know that any of these things, I don't even know that display person is going to use standard input output. All I've been told is display person displays person. Probably should have had a better comment there. I should have had more information there, but either way, display person is going to show someone's information. And it's definitely coming out here, yet I do not have standard input output. Because in here, where the code needs it to be able to run, it includes the libraries it's going to use. So this thing It's using the string library for string copy. It's using the standard library for malloc and free, and it's using the standard input-output library to, where is it here, do printf. Right, so only at the point it's needed is the library included, and the main doesn't even need to know that the library is being used. All it's saying is person.h has told me it can do certain things, and I'm going to trust it to do certain things. And so all I do here is I call these functions that have been provided to me here, and then in the person.c here, it's actually going to grab all the bits and pieces that it actually needs. So it's an interesting it's an interesting kind of way of doing things. People are discussing this. I'm going to assume that Dean is discussing that with you, and so there are answers to any questions that are happening there. All right, let me go back to what we're doing there. And so there's some slides here talking about the multi-file project, but as I've gone through and shown it to you, anyway, I don't think we need to go through these particular slides. Yep. So we talked about compiling. Oh yeah. When I kind of said this before, but I'm going to reiterate. We're going to be keeping multi-file projects pretty simple. I am going to run through them again. Don't worry, this is not the only time you will see them. We're probably not even going to put them in tutorials this week. Next week. We're going to look at it later. But I did want to at least show you this kind of layout, because the second assignment is going to start with multiple files. And so I did want to show you at least this simple layout so that we can look at it later. You're not ever going to need to create a multi-file project. When I say ever, I mean in COMP1511. You're not going to need to be able to create a multi-file project, but you will be using them. So we will show you at least a little bit about how they work. And we're going to use them again, so don't worry if, like, it's always going to be like this, right? The first time I show you something is going to be a little bit like a hammer to the face, but then we will we'll use them again and again and again, and you'll get a better idea of what's going on with them. Okay. So it's 11:02, so we should definitely wrap up here. Today we looked at functions in memory, looked at memory allocation. So we looked at the idea that we can grab a piece of memory that doesn't get automatically cleaned up by our bracketing system, our scoping system, which means we can have stuff that lasts longer than the functions that it works in. Then we also looked at multi-file projects and how we can connect them together. And just sneakily, look that I've done that here, that I have a function that creates a person. So here we have person Batman is create that person. So then I now have a variable here, and the reason that I can create something that I can then use after the function that created it is because I've memory allocated it. So I've done sizeof, I didn't actually need a space there, struct person. And so I have a struct here that has a certain amount of information, and sizeof has allowed me to know exactly how big this variable type is going to be, struct person, and then I can memory allocate it. So I'm already using some of the stuff that's there. So this demo is available. You can have a look at it and have a quick look, at least for yourself, at how the structure works between the main file that includes only the H file and only calls functions that it can see in the H file, and how the H file and the C file are kind of related in that every function that is declared in the H file will have a matching implementation somewhere with that same first line in the C file, and that's how we have completeness between them. All right, I'm going to wrap it up there. Sorry, I've gone 5 minutes over time. I will just go back into break mode for a second, then I'll come back. And if anyone wants to stick around and ask questions, I'll stick around for a little bit and answer everyone's questions. I mean, I'm going to assume that Dean's already answered a lot of your questions, but I still think that I'll come back and talk to everyone after a quick break. Alright, didn't really need to break for that long anyway. I just had a quick drink because my throat is not really surviving the me talking for 2 hours straight. So, any questions that anyone has that Dean hasn't already answered, throw them in chat now, and I will go through them. I've dumped a fair bit on you today as a welcome back from flexibility week. Now I have 2 topics in 1 lecture. But you don't have to know them all perfectly yet. We're going to definitely go deeper into these things before you need a complete understanding of it. And we had discussion about what constitutes a superpower. Obviously, being able to talk like this is a superpower. Just a joke, really. I guess that's the famous thing about Batman, is that he's a normal human in amongst all these superheroes, and so all he has is his ingenuity and his wits. And also, like, years of martial arts training, which I'm sure helps. Michael's saying, you missed the beginning. What happened with the YouTube solution to the assignment? Did someone in the course make it, or was it just a coincidentally similar video? You probably just want to go back to the start. Once this gets uploaded, you'll be able to watch the beginning. So I did talk about it because obviously it's not an ideal situation to have someone publishing the solution to the assignment on YouTube. The TLDR, the takeaway from it, is me saying that you decide what you want to get out of the subject. If you want to get learning out of the subject, then you probably want to ignore that video so that you can work through it yourself, because working through it yourself is the major part of doing the assignment. If you're not working through it yourself, you may not be learning everything that we wanted to teach you from the assignment. So I think for everyone, when there is a kind of difficult temptation like that put in front of you, you want to weigh it up against what your own goals are. So if you've got particular goals that you want to achieve, you got to think about how you want to achieve them. It's usually going to be something along the lines of, I want to get better at programming. One does not get better at programming by copying someone else's code. One gets better at programming by figuring out what to do and putting it into practice. So yeah, it's out there. There is, of course, behind the scenes official stuff happening with that. That's not my business. My business is educating the people who want to learn, rather than going on a detective investigation to figure out where it came from and who's doing it and all this kind of stuff. That's not my problem. That's someone else's problem. Yeah. I'm not even going to ask where that's going to go. I've just passed it up the chain and someone else will deal with it. Taylor's asking, is using multiple files a bit like when no one in the group project has any idea what the others are doing, but it still miraculously comes together? Taylor, 100%. That is actually what we do. So when we're working on a project, let's say we were working on this kind of superhero project here, you could very, very easily have one person working on this C file, another person working on this C file, and both of them can see this H file which they've made together in advance, and they say, okay, this is exactly how this thing's going to work. So the H file is an interface between 2 C files. And the beauty of it is, so long as everyone agrees on that interface and works on that interface, you don't need to know what the other person's doing in their C files. You just trust that everyone, when they hit that interface, is going to use it the way that's correct, in a sense, so that the person writing the high-level program that's going to do all this stuff says, I trust that the other person, when I call display, is going to make sure this thing displays. I'm not going to check whether it does or it doesn't. I'm just going to use it, and I'm going to trust that it works. And this person here is going to say, I trust that this person is going to use these functions. and they're going to use these functions. I'm going to provide the functionality that we agree that these functions are going to do. So this one here that's going to free a person is going to free any memory used by that person, which is pretty simple here. It's just going to call free on that pointer. But if there was more information, if there was something else going on, let's say the person had a sidekick included, and then there were two memory allocations going on. There was the person and their sidekick. Then I'd need to actually free more than one thing here, but I would be saying, look, I'll deal with that. You don't need to deal with that. You just think about using stuff, right? And so this person is the person that's working on the flow of the program, and this person's working on the nitty-gritty of each of the functions, and they don't really know what's happening with the flow because they do each of their functions in isolation like that. So we could totally split this up, and then when it comes together, so long as we worked to the same interface and no one comes in halfway through and changes this interface without both of these people knowing what's going on, then we do get these group projects magically coming together. So this is why we actually put a lot of time and effort into design of our programs before we start writing them, because we want to design this interface here between the two really, really well before we start doing anything. Because if we don't design it well for everything we think our program's going to do, any change we make to this mid-flight, everyone who's using it needs to know about it. As opposed to, if this is locked down before we start working, then we literally don't need either of these people to see each other's code at all. We can just use the H file. That's a really good question, and I wish that I'd talked about that during the lecture now. But thank you for asking it anyway, Taylor. Hopefully some people will still see this. Charles is saying Stack Overflow programmers would argue otherwise, talking about the difference between copying code just to get a result versus actually learning things. I mean, the way that we code in a university is so different from... Well, actually, it's not. The reason why we write code in a university situation is very different from the reason we write code in a professional situation. In a professional situation, the reason we write code is to have stuff that works so that we can ship it. You know, we want to be able to ship code that works. And so often we're going to look up Stack Overflow and go, okay, is this going to work? Does this actually work? I need to know. And I need to see that someone else has tested this, and then I can use it and stuff. As opposed to like when you're working as a student, as I said at the beginning, I don't need you to give me a solution to the assignment. If I want to, I can spend a few hours, and then I'll have my own solution to the assignment. I'm not using you as a workforce or anything like that. It's not for my benefit that you finish the assignment. It's entirely for your own benefit. So what I do when I write an assignment, this wasn't written by me, this assignment was majority written by Dean actually, but I do the overall structure. It's kind of like in the assignment, I'm at this end and Dean's at this end, and we work together as a team. So I tell him, okay, this is what I want the assignment to be able to do for people, and he says, okay, let me look at the nitty gritty and make sure that the educational goals fit together for us. The thing that you want to get out of the assignment is the fact that you pieced it all together, not the final result. The fact that you worked through the problems and solved the problems, all of those things are the goals that you have for the assignment, not to actually finish things, but to figure out what you've learned from it. So you learn by, especially in an assignment, you learn by the practicality of doing it, the practicality of thinking around the questions that I give you, and then being able to come up with your solutions to those questions. So if you watch a YouTube video and then you just use someone else's solutions to it, you might as well have not done the assignment, because it doesn't help you then. So the only difference you'd get there is you get marks. And I do understand for a lot of students that the getting of marks is important. But in the overall scheme of things, getting marks is only important up until you actually have to start programming professionally. And then when you start programming professionally, if you got a lot of marks but you didn't earn them, then it's kind of useless, you know. So if you cheat in all your assignments, I always laugh at this. It's like, 'cause there's always going to be people who do this. It's super expensive, so they pay money for the degree. and then they pay someone to do all their assignments in the degree. There's actually people out there do that. It's like a weirdest job ever, because you're paying someone to take away what you paid for. So you paid for learning, and then you're paying someone to take that learning away from you. So you're paying twice to get nothing. And so you get to this point where you get to the end of your degree and you've got all these glowing marks, you've got HDs in everything because you paid for everything. Although most of the time people who pay for everything don't get to the end of their degree because they just hit like one exam and they're like, oh, turns out I don't know anything. But, you know, that's a different situation. But, you know, even if they do make it all the way through, they get to the end, and then someone asks them to do something at work, and they're like, oh, maybe I need to pay someone else to do this. And then that's a little bit silly because you were getting paid to do it. So if someone else could do it, and we could have paid them to do it, then you won't get hired in the end, you know? So the whole, yeah, this is kind of what I said at the beginning of the lecture anyway. You decide what you want to do and what you want to get out of your degree. If you just need to survive your degree and you don't care what you learn from it, then yeah, I guess you can use a YouTube video that tells you how to solve the assignment, and then you'll be able to get further into the course. But you still won't know anything, so you'll get further into the course and you'll end up further behind because you didn't spend the time to practice it. And it just sort of ends up catching up with you to the point where you just don't know anything. And then you end up having to go back and relearn it for yourself. And it'll be really funny because people will come back to my lectures on YouTube and go, oh, I need to go back and learn that. I mean, for a lot of people, I think that's a good thing, is that my stuff's publicly available, so you can go back and get it later. So there is stuff in this course that you're not going to understand by the end of the course. That's just human, right? That's no big deal. But if you went out and intentionally didn't understand it, then I guess I'm still going to welcome you back when you eventually do want to understand it, when you want to watch my YouTube videos. I've got no problem with that. But I think that if you see the answers before you've worked through them, you lose that good opportunity that you had to actually get a chance to learn from it. So if you didn't take that opportunity, and you see all the answers to it, you've kind of wasted that chance. I don't know. I don't think I should keep talking about this because I think that my opinion's pretty clear on this. That I'm not even too worried. I mean, yeah, sure. There's all this stuff about academic misconduct and stuff like that as well. There's all this stuff about cheating at university, but like, that's not how I want to teach you. I don't want to teach you by going, don't cheat or I'll hit you with this big stick, because that doesn't really get people to do things. The way I want to teach you is the way that makes sense, is that the only reason that I'm here is that you want to learn something and I can help you reach your goals. And so I want everyone to be thinking more of, this is what I want to be able to do, and Mark is someone who can help me get there, and all the tutors are people who can help me get to my goals. My goals is to become an effective programmer, or my goal is to become an effective computer scientist, which is much bigger than just being a programmer, obviously. And there's plenty of computer science that doesn't involve programming. And in order to do that, I'm going to trust that this stuff takes time. I'm going to take the patience to spend the time to learn this stuff. And I know that this structure is put together in a particular way. So we will give you enough information so that we don't spoil the learning for you. And the more information that you grab from elsewhere, the chances are that you're going to spoil something. It's not always going to be the case. Sometimes you're going to see stuff online that's going to spark your interest and get you researching deeper into things. But sometimes when it's specifically tailored to solve this content, you're going to miss out on the chance that you had to solve the problems for yourself. I should move on. I just keep talking. Well, obviously I've gotten like very little work done over the weekend because all I've been doing is dealing with that bullshit, frankly. But anyway, let's move on. Okay. Okay. So, Terry's asking, wait, if you do int pointer, you declare an integer pointer, and then equals memory allocation that, then int pointer equals 10, does that mean the variable which holds the memory allocated is 10? Okay. Let's, I'm going to start a new code file to talk about what Terry's talking about, which is actually the code file I deleted. Memory demo.c. We'll just do this really quickly. So, Terry is asking, ooh, that's not going to work. Standard library, because we're doing some memory things. We're making an integer pointer called int pointer, and then we're memory allocating the size of an integer. So this is fine. This is a really standard thing we're going to do. We're going to do this heaps, where we have a pointer to something, and then the same type as the pointer is here in the size of. This is a really bog standard declaration of allocated memory. We're going to be using this. The only thing we're going to be changing is the type here. That's going to be a different type. Like in the person thing, it was a person, or it was a struct. And then we'll obviously be changing the name of it because we're going to name our variables. But this kind of structure for memory allocation is going to happen a lot. And the question was, if we did this, so I'm going to assume that you specifically meant int pointer equals 10 and not star int pointer equals 10, because these two are very different things. Star int pointer equals 10 says follow this thing to the memory and change whatever you get at the other end. Int pointer equals 10 says the value of this pointer, was the address of this piece of memory. I have now, if I've changed the pointer, I have not changed the thing at the end of the pointer, I've changed the pointer itself. This pointer is now aimed at memory location number 10. The chances of your program actually having access to memory location number 10 are very slim. Slim to basically nil, because the chances of a memory location at that low a number actually being allocated to your program is basically none. Most likely that memory location is something the operating system is using, although we're going to go really deep. We're going to do a deep dive here into this. The addresses for memory that you use might be specific to your program. So your program might have, so I had 8 gigs of memory that I could use. It might go from 0 to 8 gigs. So memory 10 might be something, but memory 10 might actually be the memory for this piece of code. I can't remember exactly how it's structured. I think from 0 onwards might be the compiled code. So memory location 10 might be this character. It's going to be compiled though, so it's not going to be exactly the same. So what we've done is we've moved this pointer away from the memory and we've aimed it somewhere else, which means this is going to cause some serious issues here, because now we don't know where that memory was. We've lost it by overwriting the address that I'd stored in that pointer. We've actually caused a memory leak here because we can't get back to this again. There's no way for us to know exactly where that was and to go back to it. So I've now overwritten that pointer and caused a memory leak. Charles is saying the same thing. Yeah, this would probably be pointing to unallocated or reserved memory, so you really don't want to do that. It's very dangerous. Terry's asking, what is the point of memory allocation if it's going to be freed at the end anyway? So let's look at what the point is, and I have a demo. I'll just open the other files. Oops, I opened the running files and the backup files as well. So let's look at this one here. I've got a function to create a person. So this function is going to give back the person that's created. So the main is using that as this Batman that it's created. If I did not have this memory allocation here, so let's say instead of that file, I say struct person hero. These two lines are not that different from each other. They're both allocating a variable called hero. This one's a pointer because it's a capital P person, which in here, put these in a different order, we see that type def struct person pointer person. So this is two things. One is the name person and the other is the type struct person pointer. So I've said person is the same thing as struct person pointer. So here, this is a pointer to a person and this is the actual variable. So if I do use this as the variable here, I need to change these because they're not pointers anymore. I'm not going to change it, I'm just going to talk about it. So I would copy the name in, say that they don't have any powers, and then return this hero. So if I returned this at this point, this would all get deleted. So this variable that I'm returning gets deleted because I've reached the end of this curly brackets here. So what happens is this variable doesn't last outside these curly brackets, so I can't really give it back. I mean, really, I would actually have to do this as a pointer to do this properly. Struct person pointer hero equals the address of. It's getting a little bit more complicated. Struct person, I'm going to just call it H, and then the pointer to hero is equal to the address of H. Okay, so now this is actually going to work with this in terms of this thing. I was supposed to return a pointer to something, and so I'm returning a pointer to this thing, and then that thing is going to get all this information put into it. This variable disappears when we hit these curly brackets. I've returned a pointer to that variable, but since that variable has disappeared, I've got a pointer to basically nothing. It might even look like it works for a bit because that memory will stay there for a little while until something overwrites it. But what I've done is I've created a variable and said, here, I'll give you access to that variable, but then the variable disappears before anything else ever gets a chance to use it. The difference between just declaring a variable like that and doing this memory allocation, so if I get rid of these two lines, this memory allocation is guaranteed to continue to exist up until I free it. So I can create it inside this function knowing that this curly bracket here is not going to wipe it away and make it disappear. It has been allocated to me, no one else can use it, so I've got control over it. So that's why we're using something like this memory allocation. So that way I can use this create person multiple times. I could go, I'm going to create Batman, Commissioner Gordon, Robin, Catwoman, the Joker, and all these other people, all using just this one function, and each one of them is going to get its own piece of memory that no one else can overwrite, no one else can use until we give it back here. And so I can set up all of these things. As opposed to if I didn't have the function to do this, I'd have to set them all up in here and it would get fiddly. So this memory allocation here allows me to create these pieces of memory in this function. This function then ends, but this memory doesn't. So that's one of the things that's really useful about it. I should delete these bits that I added on there. Yeah. So hopefully that helps you understand that, Terry. Andrew's saying I was using REPL to write all my code because it's easier to manage everything. Is that a problem? I think REPL is sort of okay. I mean, a lot of your tutors are using that so that multiple people can work on it at the same time. Just make sure you're saving that stuff somewhere, because I don't know if REPL actually saves everything that it works on. So if it does, it's fine. You can save it, and then you can copy it into your account here to use. and stuff, but it's going to be a little bit harder for all of your testing, because you're going to get you're going to want to test stuff here in our systems. You just have to press tab twice because REPL has 2 spaces indent and gedit has 4. That's the thing that we're going to get, and we're going to get that a lot, right? So 2 spaces is a standard for some people, 4 spaces is a standard for other people. Depends on who you're working with and what the style guide is where you're working, which one you're going to use. So it's always going to bounce around depending on the work that you're doing. And Charles is saying you can probably change that in config. There may be something in REPL where you can say what the tab is. Because if we look into the preferences here for gedit, bracket matching, text, maybe the tab width. So I could change the tab width. I'm going to leave it at 4. I don't know for certain, but 4 is usually a very accepted standard in programming. So not everyone, and I'm never going to say everyone in programming because there's so many people doing different things in programming, but the average most of the time is people who use 4 spaces for the tabs. There's a world out there of people who use 8 spaces for tabs. That's an older thing because it really pushes things along and makes things very hard to read. 4 means that you're less likely to have ambiguity. So you get this thing where this is 2 spaces along, but this is further along, so you can see the difference between them. If we've got 2 spaces, it's sometimes easier to get lost amongst things like that. I mean, I would accept an argument if someone said we're using 2 spaces in this organization, and I would be happy to work with 2 spaces. I don't have a strong connection with the 4 spaces. We just use it because it's a reasonably standard thing to do. Oh, it's like down here. So that's really easy. Yeah, I could have just changed that down there. I've never actually looked at that bar. I use this part of the bar, definitely, to know where I am sometimes, but I haven't actually noticed that it's there. Ooh, we can change it to different languages. This is just changing the syntax highlighting, by the way. It's not going to magically translate your C code into something else. Okay. Andrew's saying you can. Ah, there you go. That would make things easier in gedit. So now you're going to have to reprogram the reflex that you've gotten into for double tabbing everything. Terry's asking, was person the pointer or the hero? So person, both, it looks like both Terry and Charles are asking you about typedef. So typedef is interesting. Typedef is a C keyword, and what it says is that I'm going to give you 2 things, and they're both going to be types. Generally, one of them is going to be a type, this thing. I'm going to put some space in between these because everyone, when I first show this, always gets confused and thinks that this is one half and this is the other half. But I think that we've done a bit of pointers now to know that this is a type. The star is a type, and it is attached to the name of the thing because if you declare multiple of them at the time, you need to remember that only some of them are going to become pointers. So typedef says this is a type. This is a new thing that didn't exist before now, but it is now going to be a representative of this. So we can now use either capital P person or struct person pointer anywhere we want. And what this allows us to do is it allows us to pass stuff to our main as this capital P person. This capital P person is an abstract concept of a person. It is not something that says that you have a pointer to a struct, because in this main here, if I was to say struct person pointer here, this would be me implying that you have a pointer to a struct. You don't actually have a pointer to a struct because the main.c does not know what this struct is. So the implication of me having struct person pointer Batman here is that I could do something like this. Batman name equals Bruce Wayne. This is not even legal C. I would have to do a string copy to do this, but it's the idea that I could try to do something like this, except my main doesn't even know that this exists. My main does not have access to the fact that there's a name and a list of powers. Oh, check it out. Two-dimensional array of characters is a one-dimensional array of strings. So this is something that's really useful. So if you want an array of strings, it's just a two-dimensional array of characters. But here, if I was to leave this as a pointer, as a struct person pointer, it implies that I could do stuff with it, which I can't, because I don't know what that struct is. So it's better that I hide that behind this abstract variable type here that says, if I'm going to think about this, I can't think about it as a pointer because I don't have access to the pointer. All I have access is this capital P person, which I can create, and then I can use it as input to these functions. If I use it as input to these functions, when it goes into the function, it knows the struct, because where these functions run, they have access to the struct. And so what I'm doing is I'm saying that the C file has access to the struct. No one else outside has access to that struct, so they shouldn't be playing with it. They should be using just these functions. And if you only use these functions, then we guarantee, because we wrote the implementation of those functions, we guarantee that you're never going to break the struct. If we break the struct, yeah, fine, but you can't break the struct because you don't have access to it. So it's like a safety measure. It's like, for example, going back to the analogy of driving a car. If I press on the accelerator pedal for the car, my very, very vague knowledge of how cars work is this changes how much fuel goes into the engine. It's careful about this. It mixes the fuel with the air properly so that it actually explodes correctly inside the engine to create the energy to drive the car. If, for example, I could access the engine itself and I tie a piece of string to the valve that changes how much fuel goes into the engine, and I just yank on that piece of string instead of pressing the accelerator, I can easily put the wrong amount of fuel into the engine, either causing it to explode or flooding it so that it doesn't work at all. So if I had access to that, I could make it go wrong. As opposed to, I only have access to the accelerator, and then something else is between the accelerator and the engine itself to make sure only safe usage works. That's what you can think of here. And that's why we have this type def that says, don't think of it like a struct person pointer, because you don't even know what a struct person is, so you shouldn't think of this as a pointer. You should think of this as this abstract type here called a person. We're going to go into more detail of what abstract types actually are. I'm using the keywords here. There's a thing called an abstract data type. We'll talk about that later. So hopefully, Terry and Charles, that gives you a bit of an idea about why this type def exists. Because when you think about it, there's no reason why we're just renaming a type. But when it comes down to it, the reason we're renaming it is so that we know, or we can see it clearly, it's not a pointer. We're not going to use it as a pointer, even though technically it is. But the only thing that can use it as a pointer is here, in the C file that knows what it's pointing at. So we've protected that knowledge in a sense. Charles is saying 5 space gang rise up. Let us never reach that level of chaos. Negative tab space. Did I say Bruce Wayne? Well, that's how you know it's not Bruce Wayne, the eccentric millionaire. Yeah, Charles, if you come from a language that has private and public, you could think of it as the fact that what's in the C file here is in a sense private, in that the only things that can see what's in the C file is the compiler. So the compiler has done the stuff that's in the C file, and then the H file is like what the other parts of the program can see, because they include the H file. And note that the the H file doesn't even include anything, so the H file doesn't even know what's in the C file. The C file does include the H file, because then it says, okay, these are the definitions of the functions. So it's kind of like the functions that are at the bottom of your program, below the main, they have seen the fact that the functions were declared originally. And this is what this is doing here. It's saying, okay, I can see that these functions have been declared, and then I'm going to go and implement each one of these. So I'm going to give them the actual code that makes them run. So that's the kind of structure that we're using. Charles likes my explanation. That's cool. Okay, good. So that's working for you. Terry, you have a retracted message there. So I don't know if that was you saying, I don't understand this, and now you've retracted it, and now you do understand or not. Let me know if it's working for you. Yeah, Charles, what you're saying there, implementations need prototypes, but prototypes don't need implementations. Actually, technically, they don't need each other at all. So if we had this C file, and we only had these functions, like so, and we had the struct, and we actually included the C file here instead of the H file, technically it would work. We would then have given up all of the safeguards that we had with having this interface between the two and having the type def and stuff like that. Actually, it wouldn't work because we couldn't use the capital P person. We'd have to also include the type def. But it would be technically possible for us to say all of these functions are just dumped here. So if we did this, super, super dangerous, don't do this. But we could technically, so this is just answer your question, that the implementations don't actually need the prototypes, in a sense. It's good for them to know about them, because that means that if we're including the H, then we can see everything that the H was intending for us to do, which is important, because if we don't see it, we don't know what we're going to do. But if we were to skip this interface middleman and just put person.c into person.h, we would have access to all the functions. We would also have access to all of the inner workings, and we could then use it unsafely, in a sense. So there is a way. That's like just implementing all of your functions above the main. So it's like copy pasting these functions here into the main. Actually, that would 100% work, because we would get the person.h from the person.c, because person.h does that. The downside to this is now the safeguards that we had to hide, for example, this struct here, are no longer there, because now the main has full access to everything that's in the C file. And it's potentially dangerous, because that stuff I was doing before, where I start to treat the person as a pointer, and I start to dig into this stuff and make changes inside the structs, means everything that we did, I'm going to put this back, because I don't like it, it's like super unsafe. Everything we did to say that you can only use these functions to make stuff goes away, because then you could actually just get into the struct and make those changes. Whereas all of our implementations of these functions make sure that, for example, if we give a power to someone, we are doing the string copy, but we're also keeping track of how many powers they have, and we're keeping track of the number of powers someone has, so that when we display it, we will display only the powers that we've actually given them. As opposed to if we didn't do that and someone had access to the struct, they could just put all these extra powers in that would never get counted properly, or they could change the number of powers someone has without putting the strings in, and then we'd get these weird garbled rubbish strings for their powers. So this function here guarantees that we're always doing it the safe way, and this interface with the H guarantees that no one can bypass that safety measure, because no one else can have access to this struct other than the code that runs in the C file. So that's part of this whole thing. We're going to go deeper into this, right? But yeah, this is Charles is saying this is just literally manually doing the work that a smart Java, C# other compiler would do itself. Yeah, there's a reason why we do C. Because if we were to do this in, say, C sharp, which is actually really similar to C and has some of these same structures, if we were to do that, you would get a vague idea about what's going on, but you don't get to see when it doesn't work because it's so safe that you don't get to kind of experiment. And when we think about it, when we are getting stuff wrong, when we're seeing these things that don't have the safety net, because we don't always 100% need safety nets when we're programming. I mean, it's good to have, especially in an industrial sense when you're trying to just go quickly and get code to work. When we don't have the safety net and we can actually make this stuff break, we're going to learn a lot more about how it actually works under the hood. So if we'd been teaching, and this is like totally possible, our first programming course, if we did it in Python instead of C, we'd be jumping at least 2 decades, possibly 3 decades between when these programming languages were created. And Python is a much more efficient language than C because it just handles a lot of stuff for you. But when you're not having this stuff handled for you and you're having to do it yourself, you're going to learn more about what is your actual connection with a computer, which is why we do it this way. I would fully accept arguments for not doing it this way as well, because if you wanted to, you could learn programming with something like Python first, and then never understand what memory is. Like, you could literally not understand what computer memory is, and still be an effective Python programmer. So you can see the reason why I'm teaching C instead, is because I want you to understand a bit about the architecture of the computer, because some of you are going to need that. Some of you are literally going to be doing stuff with computer architecture as your entire careers. So this is why the grounding is in a language that allows you to actually break stuff by accident, because there's definitely something to be learned there. Charles is saying you miss C sharp. Safe by default, but you can do some unsafe stuff. Yeah. So if you want to be masochistic, you can make it unsafe. Whereas if you want to be really masochistic, you just always program in C. It's never safe. Or you program in C and you use GCC instead of DCC. So GCC is a compiler that just literally lets you do whatever your code says you're going to do. You could turn off all the warnings in GCC as well, and then you can just dance through memory, changing just other pieces of memory, and it's super, super unsafe. You can just walk off the end of your array and change whatever variable was after it. DCC at least is going to say, hey, this array was allocated like this, and you've gone off the end of it. Are you sure? Like, because I don't think you want to do that. Yeah, so we do have a little bit of it's actually not a safety net as such. It's more of a warning sign to say that this could end up being a problem. Yeah. There's actually, I've told you this before, right? There is actually a really good way to learn assembler if you want to, and it's a game called Human Resource Machine. I'm wondering how many copies of this game I have sold. I know that's not going to be significant to the developers. I'm pretty sure they've sold, like, tens of thousands of copies. So me every now and then telling a few hundred people that it's interesting, and I expect only 5-10 people at most are going to actually buy it each term. But I would love it if part of the sales of that game is from my lectures. Yeah, you'd actually learn assembly in that. It's actually assembly programming, that game. Andrew's saying DCC is like that meme where it says you can't do that, and GCC is like done. Yeah. So GCC is a compiler that professionals use, and they will use it because they already know. So they don't need the warnings. They know where the pitfalls are, and they know how to avoid them. Or GCC is used by people who don't know and fall in the holes anyway. I'm never going to say that just because someone is a professional programmer that their code is perfect. I learnt this when I came back and started teaching again, that a lot of the stuff that I'd built as an engineer was just flat out unsafe. had memory leaks in it, and had a whole lot of issues. Was like at a low level just coded flat out incorrectly. And it was really funny that it wasn't until I went back and taught the basics and I was like, now I actually understand C. I was using it without a full understanding. I worked with a C++ developer for a bit, right? And I was definitely using it without a full understanding of everything in it. And then coming back and teaching it, I actually know it better than I did before. So it's interesting coming back to these fundamentals. Yeah, and Charles is like talking about segmentation fault. Be happy that you're learning programming without ever seeing the words segmentation fault. Because segmentation fault just means that you've done something weird in memory, and it doesn't give you any other information than that. It just says that the program broke because there was some access to memory that shouldn't have happened, or there was creation of something in memory where it shouldn't have been allowed. There's many things that can cause a seg fault. Like, the fact that I say seg fault means you know that I've seen this so much that I shorten the name. DCC at least will try to tell you what went wrong so that you can learn something. Okay, I'm going to wrap it up. I've turned this into a 3-hour lecture, and I think I'm now just spitballing on random stuff. So thanks for hanging out, everyone. Daniel Mansfield has been pinging me about a Friday evening thing, so his chill out stream. So I might actually be turning up in his chill out stream, not just as a participant, but I may turn up on screen as well. So we may do something like that. We'll see how we go. We may be able to turn it into another one of these Friday things where we he does his stream and then I'll start my stream afterwards and we'll hang out and chat and stuff like that. We did that a couple of weeks ago. It might be fun just to hang out and chat. Charles, yeah, is saying DCC is so good. I'm surprised it isn't a regular thing outside UNSW. I think the reason why it's not a regular thing outside UNSW is it's a little bit fragile. If you ever meet Andrew Taylor, and if you're continuing in computing, you will definitely meet Andrew Taylor. Have a chat with him about what DCC actually is in the back end. It's one of the most complicated programs I've ever seen. I took one look at it when I'm not going any further into that. It's running, I don't know how many different languages. I think it's running 3 different languages, and it's multi-threading. So threading is where you can run more than one program at a time. It's multi-threading, code analysis, 2 different compilers, memory checking, and an interactive debugger. I don't know, but I think it's doing all of that at the same time, or it's doing something else funny, which is that every time your program crashes, it stops it and it starts it and runs it again up until a certain point so that it can tell you what your variables were. I don't know exactly how it all works, but it's full on. It's really full on. So I think if we were to release it publicly, it actually is available publicly. So there's a Git repo where you can get DCC. I don't have the link on me, but if we were to release it publicly, I think a lot of people would be like, this is so volatile that we don't think this should be used in production. And I think that all of your programs take a lot more resources to run than a standard program would with DCC. So it's very good for learning. It's very good for seeing what's going on. It's very, very bad if you want your programs to use the minimal amount of computing power necessary to run. So a little bit back and forth. Charles, yes, it embeds GDB, Valgrind, GCC, and I don't know, but I think Clang. So I think it is simultaneously running 2 compiled versions of the same program. I can't remember. It got complex enough that I was just like, Andrew, I'm gonna let you run this thing. You're the one that likes playing with compilers. I'll use it, but that doesn't mean I want to understand. Okay, thanks for coming all. And yeah, Charles, yeah, maybe not DCC itself, but a similar, safer kind of compiler. I suggest Clang is not a bad idea. Clang is a more modern compiler than GCC, and I think it has better warnings. I haven't really used GCC in such a long time that I don't really know, because I think I moved over to Clang, would have been like 4 years ago, and I haven't used GCC since, so I don't really know. Also, I don't write any kind of complex code like I used to. You'll find that, like, this is what happens to a professional teacher, is that the more time I spend teaching, the more code I write, which is like the first half of a program. I just write the first half of a program, let you write the rest, and I write the first half of another program, let you write the rest, and this kind of thing. So I actually haven't done any kind of big projects like I would have when I was, like, full-time programming. So yeah, so it's actually kind of interesting. Anyway, I'm gonna let it go here because we've got a full hour over the lecture time. And I will see you all on Thursday, and I'll let people know what's happening on Friday as well. That's going to be completely chill social. It's not going to be not going to be any kind of official subject content. So I probably won't necessarily put it in the subject page or anything like that. But I might just publicize it on my stream. I'll just put a public link up when that happens. And if not, you can always go to Dan Mansfield's stream first, and then we'll bounce across to mine afterwards. If we bounce, we may just stay in his stream for the evening, but we'll see how we go. Alright, see you all later.